welcome to another coding session. Last time we designed a new type system, and this time we're gonna implement that. Yeah, we have a lot of work to do, so let's get right to it. So the idea was basically that we have structs with this end symbol, that we have enums with this pipe, and that you can actually specify types in the language. And yeah, basically this allows us to then have function signatures with types, and that allows us to have function overloading based on the types of the values. Yeah, oh right, before we even get into that, I think, hang on. I think it doesn't compile anymore because I changed some stuff in the Martinaise standard library. I mean, like, that's the trade-off that you get from depending on an unstable language, but at least it's my language and I know the breaking changes. So right, let's just see what fails. Like this, I think. Run compiler breakfast. Yeah. So string got renamed to still got renamed to string, and vec got renamed to list, just to be more intuitive. Yeah, that means that this right here will be a string, and does anything in here change? Or we can just do this. Oh, I mean, that's pseudo test code anyway. Okay, we have these, we have these. Yeah. I could just like change every occurrence in the project, but I'm not sure of that. No, I'm not like string. Boom. Sure. And also vec with list. Change all. Okay. But we probably need to. Oh, those are all saved. Okay. So we have stuff. Let's actually try to compile that and commit that if it's to reverse to string. All right. Oh, yeah. And the standard library, we added a to-do thingy at some point, and I haven't migrated that yet. So let's wait, standard lib stand up here. Oh, they're not sorted by name. That makes sense. Yeah, there should be a string. Okay, sorry about that. So this is more like Martinaise internals. Yeah, now everything should just work. When compiling main, wait, main uses still. Oh, right, the string literals, so I still need to make that. Build the newest compiler. Takes a long time. Well. Strange. Okay, so now things kind of work. The to still got renamed to string. Now, almost. Yeah, is there a lowercase vec that should be replaced with lowercase list? Sure. And I'm also looking for to still. Okay. Perhaps now. Wait, where's that? I think I should test the standard lib a bit more. Iter, yeah. Vec, yeah, please rename that with list. Okay, okay, true. Store builder gets replaced with string builder. Yes, indeed. Okay, okay, cool. This worked. Yeah, sure. Like this kind of thing, like we don't support syntax for defining enums or structs yet. So this, definition of something weird is expected. Okay, so I guess the first thing would be to push the fixes to the standard library. Fix some string back usages. Yeah, and just push that. Yeah, basically all of the Martinaise files. I mean, sure. That wasn't generated. This maybe. We'll leave it like this. Update to string list. Okay. Yeah, so sorry about that. So the standard library of Martinaise is not stable because of me. Well, okay, but now everything works again. So now we basically need to think about how do we handle types? How do we handle defining types, like separating them between like uppercase and lowercase definitions? Like we need to treat this and this differently, basically. We also need to like handle those types, like choose functions based on the types and see if the types match and stuff like that. So I think we have our compiler pipeline, and we'll just work our way through that from the top to the bottom. So we'll start with okay, this is basically just the lines of the file in a tree according to the annotation. That doesn't change. The abstract syntax tree changes. Yeah. In here we basically need to parse types now. So let's do that, I guess. Yeah, where's our test thing here? I think for like in the beginning it makes sense to be a little bit more strict about how stuff is organized. I think just having only supporting this is fine for now. So this needs to be like a separate kind of node from the children. Yeah, it's a bit more verbose. We can again, the syntax, we can change that later on. But yeah, I think this is just easier to parse for now. Right. Yeah, I'll also remove all of this into this, I think. Yeah, just and maybe we'll start with a simpler example. So we have a bool which is an enum, so an OR thingy with two variants, true and false. And yeah, let's just have that bool form. Then we have a main function which accepts an input, which is an int, and it returns a bool, for example. And let's just say it always returns true. I mean, this is enough to have some basic type checking and stuff like that. Okay, so yeah, this doesn't work because in here we expect an expression and this is not an expression. So yeah, we basically need to, if you have some lowercase definition, we need to parse this thing differently from this. Because here we allow enum types like this. We allow struct types like these. In here, if you define a struct like this, you have to provide concrete values. In here, you don't. In here, you have to provide types after that. And also in this thing, like you can do anything. You can like switch over some value and do stuff. And that is explicitly not allowed here. In here, you can only, like this is only an alias for this single type expression that comes after. Right, so yeah, let's maybe yeah, let's think about how to do that. So we have the toast, which parses stuff. And here we already need types, right? Yeah. We have a toast def with a name, and the value should not just be any toast. Oh wait. We basically have like separate contexts, I think, for types and for normal value expressions. And those top level things, they are like in yet another context. Because in those top level things you can't have this, for example. Yeah, I think we need to adjust this to, like this is a toast, something on the value layer basically. And then we have something on the type level, which is either an enum with a vec, I guess. Oh, sorry, a list of toast variants, where a toast variant has a name and payloads, args, which is a list of toast types. Yeah, and yeah, I'm choosing a list here. We could also just use a map, I guess. Yeah, why not? Let's inline this to a map from toast to slice, I guess, of toast type. Yeah. Yeah, structs. I think we don't support structs for now, because you can also just say, well, I want to create a tuple with 3 and 2 and 3. It doesn't have named fields or anything like that, but on a like type theoretical information theory perspective, it has the same amount of information. Okay. Yeah, is there anything else? We have enums. We have oh yeah. Basically, I think it's also a good idea to define built-in types and built-in functions and stuff like that in the language itself, so that they are type checked. Before we just magically had a built-in add function scope, and I guess that's kind of fine, but this should basically just be treated like a normal function, like from all of the for most of the compiler stages, because this function needs to have overloading based on the types and stuff like that. So I think it actually makes sense to define something like this in the standard library, and it just says, I don't know, magic compiler with it, and this is like a keyword or something. Yeah, because then all of these, like later on, jump to definitions still works for these, and I'm just like thinking, it would be weird if int is just there. You know, it's just magically in the language and in scope, even if it's not imported. But if you say int is, you know, magic compiler built in, I don't know. Yeah, so magic compiler built-in is like a built-in thing that you can call with a string, I guess, or a symbol. Why not a symbol? Yeah, and then this gives you a new function or a new type. Yeah, so we want this to work as well. Okay, yeah, maybe let's put these down here. Yeah. Okay. Yeah, slice of toast type. Okay, so yeah, that's basically what I was wondering. We have an enum. But what other kinds of types are there? Because in enum, you know, those kind of multiple, they have a slice of types as arguments. Is there anything that is not an enum? This is an enum, although with weird syntax. JSON is an enum. Even something like list, for example, you know, for now it would just be like an enum with one variant called, I don't know, list, that then contains the buffer like this and the length, but as unnamed things. So I think for now each type is an enum. That's weird, but okay, I guess I can live with that. Okay, yeah, and then this global toast thingy basically is just a list of definitions, I think. Defs is, you know, a slice of toast def. And we will probably have to do something toast var, I'm gonna call it. You know, inside of functions you can only define variables. You can't like define multiple helper functions inside of a function and then use overloading on them and stuff like that. I think it's just inside of functions the behavior is different. Not all functions are like globally in scope and unordered basically, but inside of functions things are ordered and you can only store you can only store like specific values. You will at some point be able to create closures, so you can store functions, you know, but not like overloading and stuff like that. Okay, so yeah, let's kind of review this. A definition is again, I don't really like this. Sure, okay. A definition has a name, I guess, and a kind. And there were basically two kinds of definitions. There are type definitions. They just define a toast type. Oh, yeah. Built-in is also a type. You know this magic compiler built-in thingy? Yeah, so they are either a type or they are a function. Yeah. Yeah, basically this. Toast fun. Yeah, okay. Yeah, I guess. And we have types and we have funs. And a toast fun has params, which is a slice of toast param. What's a toast param? Well, it has a name and it has a type. So toast type. It has a return type and it has a body. Hang on, is this? Yeah, it's like really long. Okay. Yeah. And then it has a body, which is, you know, toast, just a toast expression, I guess. Toast value. Yeah, let's go with value. The type layer and the value layer. Okay, and a function is basically has params, has a return type. Those are all, you know, you can, the idea was that you can figure out the return type of a function just by looking at the signature. You don't need to look at the body. And then the body is simpler, it doesn't have, you can't define functions. So basically in here, the top level is treated differently from what you have inside of here. In here, you can't like define functions like this. I think you can't do that right now as well, because this was just, it just resulted in an error, I think. Yeah, you know, just panicked. So actually parsing these differently and handling those differently, I think that makes sense. Yeah, speaking of parsing, we now need to parse the file into this kind of structure. Oh yeah, the writing, we need to adjust that, because of course we do. So when we write down toast, I guess what we really want is just printing all of the definitions, right? So for all of the toast defs, we want to write that definition. I mean, but there are only like 2 kinds of definitions. So actually, let's just do that inline right here. We first write the name of the definition. Okay, and then, yeah, I see. For functions, things will be different. Yeah, then we switch on the definition kind. If it's a type definition, we do some stuff. If it's a function definition, then we do other stuff. And I'm just realizing types also need parameters. Types need parameters. Yeah. Okay, sure. Let's it has params, which is just a slice of strings, because we know the type there, they must all be types. And then it has the let's call it maybe toast type def, you know, like this, and then it has the value of the definition, but it's actually like a type. So toast type, and this is either like a built-in thingy, or it's an enum, or it's a name of like a call or something of an existing type. You know, you can do, I don't know, I define map with key value as something, and then I don't know how that looks, but in here you can just say, well, I want a map from int to int. I want to store that in the true variant. So this is like a call or reference or something else. I'm going to call it call for now. A call of another toast type. Toast type call, I guess. And toast type call has a name, which is, you know, the uppercase string that's up here, and then the args, which are a slice of toast type, which are basically these right here. Okay, cool, you can have that, and you can also like reference those variables. In here we have, I don't even know how that looks, you know, but basically we can refer to them like here. This also has to be a type. So that this can also be a variable, a reference to a lowercase type variable. Yeah, kind of like that. Okay, so yeah, toast types, they actually do have some different kinds of values in there. I mean, we could also, I like that you have this in the language, but maybe we can do that later. Yeah, I'm gonna add it to the, I think we do have a to-do list, right, in the README, down here, yes. Have some way of defining compiler built-ins in the language, of like explicitly referencing compiler built-ins in the language itself. And then, you know, something like this. Okay. Sure. So, okay, this got a little bit more complicated, but that's fine. For a type definition, we now want to write all of the arguments. So for all of the parameters, sorry. For each parameter, we want to print a space and then the parent, which is a string. Then we want to write an equal sign. Yeah. And then we want to write the actual type. You know, so definition dot type. Yeah. And for function definition, well, we do something quite similar. We print all of the parameters. We print an equal sign, and then we print the, well, okay, it's not quite the same. And this is also not the same, because we print the parameter name, colon, and then the parent type. Yeah, then, not an equal sign, but like an arrow, and then the return type, then an equal sign, a new line, and then basically this. Body, I think it was called. Yeah. Yeah, body, which is a toast value. which can just be inline, by the way. And yeah, cool. Yeah, I think I like that. Okay, so then we don't need this. Nope. We can instead write a slice of toast values using an indentation. And yeah, I'm not going to call it expression, but value, because I think value is more clear. Yeah, if it's not a body, then we do stuff, and then we switch on that and print thingies and, you know, all of the things that we did right now. Yeah, functions don't exist at this point. Yeah, because they are handled like one layer above. Okay, so yeah, this will hopefully compile. It does not. 208. Oh right, yeah, when we construct all of that, like, that's totally messed up. Okay, yeah, we convert a bacon to toast. So this is the root of the tree. Yeah, actually we need to handle those differently. The top level things, they will have a different, you know, to toast. This is basically to toast value. And that's nice and all. But now we basically now we basically add one layer above that to toast type of a bacon. And to toast on bacon, which will just return a toast. And basically, you know what, let's actually have these ordered in the same order that we ordered the definitions up there. Oh, right. Yeah, I think there's a lot of things we need to do. Okay, so we have a parser that can parse thingies. Yeah, and then we have to toast. Well, let's call it. I see. Yeah, okay. Let's leave that here. And basically this can't happen. So I'm gonna add a to-do. Ouch. Yeah, we can like fix that later on. Yeah, this is not okay. This is like parsing of values. We parse an expression. Sure. Okay. So basically the question is, okay, let's actually just copy this down here and then adjust this and like strip out everything that we don't want. So bacon is a bacon, but we know that this should be the root bacon of the file. So bacon.line line.is empty should always hold. Otherwise we panic. To toast was given non-root bacon. Okay. Yeah, we don't handle like percent switches and stuff like that. But instead we just create a parser and we say, well, we want to pass an expression. No, that's not what we want. We want to pass parser.parse type def. If that's some definition. Oh. Yeah, see. So basically we want to have a list of definitions, which for now will just be an empty list of definitions. And then we just iterate over all of the children of the bacon. Well, yeah. And we basically parse each one of them. And when doing so, we then add things to this list of definitions. And then in the end, we return a toast with defs being defs to slides. Yeah, so we try to parse a type definition. Yeah, this yeah, sure. Handle type def if parser.parse fun def is some def. So we try to parse a type definition and a function definition. This is uppercase, this is not uppercase. And then yeah, this I'm just gonna comment this out for now. Yeah, and then basically we want to add things to the definitions in those switch thingies, and then in the end we return those. So the question is, how do we parse type definitions? How do we parse function definitions? And like basically we need to just define those functions on the parser, similar to how we did all of this. So we can parse expressions, we can create a definition. Interesting. Sure. We may refactor those, but anyway. Yeah, so we have a fun parse type def takes, let's add that here next to the other parse methods. So it takes a parser and it returns a maybe of a type. Actually, you know what? Let's just define parse type first. Yeah, it maybe returns toast type. Yeah, I mean, we can reorder those later on. Okay, so how do we do that? It's basically similar to parse symbol in that we want to check the current character. If we're at the end, we return none. And then we ensure that this is an uppercase character. And then we parse the identifier. Oh yeah, do we allow spaces is the question. I think here there's parse atom. Yeah, parse type atom. Yeah, basically we know we are in a type context and now we want to parse something. Yeah. So let's and we have parse type atom and parse type, I don't know, expression. Yeah. This will only parse things that don't contain spaces. This will parse everything. Right, so it first tries to parse a symbol, I guess. Because why not reuse that? Parser.parse symbol. Yeah. If that is some name for the type, then we want to return that. And we know that this is not like a call like this, because we are parsing an atom. So, you know, we can't have space separated calls. Okay, so parse symbol. This is some name. Oh. You know, maybe for now, let's only support single line type definitions. I think that makes things much easier. Yeah, let's just do that. Okay, so we can parse an atom, which means we parse a symbol, and then we return, well, yes, we just parsed toast type dot name. That doesn't exist. Hang on, toast type dot, what's it called? Dot, not variable, this is lowercase, built-in, nope. Call, toast type call. Yeah, it's actually a call without any arguments. Call is maybe an ill-fitted name for that. Sure. And let's remove this junk for now. Toast type call. Yeah, and it needs a name. And it needs args, which is an empty slice of toast types. Okay. If we can't pass a symbol, but we can pass, you know, like a, what's it called, name variable? The lowercase thing, or the not uppercase thing. Pass name, yeah. If parser would pass name, then we just return toast type dot dot variable, because this is a type variable. A lowercase type variable, okay. Sure. Then the next step would be to have, you know, what else is there? We have, yeah, we have variables, we have calls, we have enums, and we have built-ins. So if we have an enum, how does that look? An enum always contains spaces, so this can't be an atom. Okay, sure. And a built-in also can't be an atom because, you know, a built-in contains spaces. At least according to our built-in definition of this. There's a space in there. Oh yeah, actually we wanted to postpone that, so let's just remove this. Oh well, let's keep this, but this won't be passed from anything, but instead it will be added to the file maybe. Nah, let's remove it for now. Okay, so yeah, this is done. If we reach this down here, then we just couldn't pass anything. So nope, sorry, can't pass a toast type here. Then things get interesting with expressions, because here we want to basically allow these space separated things. We want to allow a buffer t to be passed. So we can't just call parse type atom. Yeah. Because this will, you know, if there's an uppercase thing, it will just consume that and not even look further. So instead, what we want is we want, well, something like this actually. You know, if we can pass a symbol, then we want to call parse type atom, because those are the arguments. The arguments are a list of toast types, and then we just loop parser.parse type atom. You know, if that doesn't work, we just break out of the loop, and if that does work, we push that to the arguments. Yeah. So we try again and again to parse an atom, and then we break out of the loop. No more atoms to parse right here. So then we return a call with the name that we passed up here and the args, which is the slice version of the args. Okay, nice. Then what else is there? There is basically only, I mean, variables, sure, and enums. Okay, so let's maybe look at variables, which I think we'll just do explicitly down here. Why not? And then enums. So if parser dot, yeah, let's maybe, sure, parse type enum, put that into a separate function, which turns maybe toast type, I guess. Yeah, if parser.parse type enum is some enum, then, oh yeah, maybe this can just directly return a map. Yeah, this right here, a map from string to slice of stuff. Yeah, so if this is an enum, then we say, well, we just passed an enum with those variants. And down here, we just return none. Cool. So how do we pass an enum? Well, basically we do something very similar to parse symbol, which means we look at the current character, if there is none, this is not an enum, and then we ensure that the character is a pipe. If it isn't, then we just return. Then we advance the cursor to consume that. And then basically we want to loop and consume all of the variants. So we basically want to, you know, let's look like this. We basically want to see, hey, first we consume this white space, so parser consume white space. Then we want to parse an uppercase symbol, so parse symbol variant name, I don't know. If there is none, then we're done, and we'll just break out of the loop. And if there is one, well, then we want to again consume white space. and then parse an atom. So parser parse type atom. Payload, I don't know, yeah, something like this. Oh, yeah, what if a variant has like multiple payloads? How does that even look in this case? Well. I think it would have to look like this, perhaps. No, like this. Which is kind of unfortunate. That really sucks. Do we allow? I mean, one option I see is to basically backtrack and say that enums have to be multi-line thingies, because then we can like easily do this. And you basically can't have inline enums. If you want one, then again, those need to be split across multiple lines. And I guess that is kind of fine. Yeah. I don't like it, but wait, so then what does type enum? Yeah, that doesn't exist basically. Yeah. Okay. Yeah, I guess it's like this. Sure. And then we have this to toast type on bacon. Yeah, what does it do? It just, I guess it just checks, am I, well, I just copied the entire function, not what I wanted to do. I wanted to check is, bacon.line, am I this? Then, well, I'm an enum. Then I need to pass my children. Otherwise, I want to pass this thing, similar to this. So I want to create a parser. Then pass a type. Yeah. Type is parser that parse type atom expression. Expression, because it can contain spaces. That is fine. Yeah. Expected type expl, something like that. And yeah, I take my children and I nope, I don't have this. And let's just ignore this for now. If this is not this, you can just, you know, if you have children, then you're only allowed to have a single symbol up here that calls these children. Yeah. So if, basically let's move this up here. If children is not empty, var type. Well, let's do this first. Let's create a parser. Okay, if the children are not empty, okay, let's flip it. Yeah, if the children are empty, then we want to parse like an arbitrarily complex type expression in this line. We want to consume white space, and we want to produce an error if that didn't work. Cool. Yes. Oh, and this is bacon.children. Sure. Else, look at this. Else, we convert the children to types, and we say parser.parse symbol type, I don't know, name, or panic expected type symbol, because of the children. Oh man. Yeah, we want to consume white space, and then we basically want to assert this as well. Okay, yeah, I mean, yeah, this is definitely like refactor worthy, but first just get it to work at all. Okay, yeah, this should only be a single symbol on that line. Then we pass the children into toast types, and then we have a toast type dot call with a toast type call with the name that we have passed, and the arguments are toast, something like this. Cool. To toast types. Takes a slice of bacon, returns a slice of toast types by creating toast types and then converting those into toast types. Okay, sure. So we do this. Maybe let's call this args, so we don't need this anymore. Wow, look how beautiful this is. Cool. Okay, yeah, I'm starting to like this. Yeah. Okay, sure. And now the remaining case is, what if this is an enum? In that case, we don't have a parser to advance. We just want to parse all of the children into types. Yeah. So basically we have a list of variants or something, which is a list of toast. Oh, sorry, no, it's a map, right? A map from string to toast type. And yeah, basically we loop over the children and we just convert them to a toast type. Yeah. Oh, yeah, we need to ensure that the line of them starts with an uppercase thingy similar to down here. So we create a parser and we say we want to parse a symbol. I don't know. Yeah, name, expected variant name. Then we consume white space, and then like the kind of hacky thing is we say child.line equals, well, child.line.substring. From 0 to, oh sorry, from parser.cursor to child.line.len. So basically we strip that from the, assume we have something like this, we just strip that up here, and then we pass this entire subtree as a type. Or in the other case of multi-line things, we just strip this. Oh yeah, this is right, we can have multiple things, multiple payloads. True. Let's okay, so this child is a variant. The question is, does this variant have all of its payload arguments on the same line, or does it not? Oh wait, it's like very similar to what we do down here. Very, very similar. Let's call this variant. I hate code duplication, but I'm gonna do this. Okay, so if it has, if it doesn't have any children, like here, then we basically say, okay, this is a variant with 2 payloads. We basically iterate over them. We parse it's empty, we just parse type atoms. Yeah, okay, we still need to do this. So, I mean, either case, we pass a variant name. That's there's no way around this, And then if we don't have any children, then we just continue parsing on that line. What do we parse? Well, we parse type expressions. We basically need to find out what are the arguments to this, so that we can then map this to a slice of toast type. What are the arguments of this enum variant? If there are no indented, further indented lines, yeah, then we just pass type atoms repeatedly. Or if there is none, then we break. Oh yeah, we need to loop. and add those to the arguments. So args.push type. Okay, yeah, we pass type arguments repeatedly, push those to the arguments up here, and then when we are done, we ensure that we are at the end of the input. Sure. And then we evaluate. Oh no, that's basically it. We're done. Okay. Otherwise, if if we have an enum variant and the enum variant has it has children like this, then there can't be anything after the enum variant. That's also that makes sense. So in this case, we have passed the name. Yeah. Okay. So now we are like, okay, this should be everything that's on this line. And then we actually pass those children into arguments. Yeah. Ooh, yeah, let's do this even more elegantly. So args will be a slice, and if we don't have any children, then we create this temporary args thingy, and then down here we say args to slice. Otherwise, we pass the args like this and just directly evaluate to the slice of toast types. And then either way, in the end, we create an enum, which will be a map. Oh yeah, which will be not here, not here. We add something to the variance, right? So variance dot put name. This right here. We put the args in there. Okay. Yeah, I like that. Beautiful. Okay. Yeah, then what do? We basically, we don't need this. No. In here, when we are done with all of our children, we now have variance, and we can evaluate to a toast type enum with those variants. Nice. Let's see how this works. Okay, there were no definitions, then pass type def. Sure. Okay. So pass or toToast type exists. toToast value, sure. Yeah, pass type def. Yeah, we have toToast type. We need to have a toToast type def. toToast type def on a bacon returns maybe toast type def. Okay, so yeah, basically we want to check if we have an uppercase start at the line. So let's, I mean, that will be similar to this, or to what's the enum parsing here to this. Yeah, we create a parser with the bacon line, then we try to parse a symbol. If that works, we know, okay, we're actually like having a toast type def. Otherwise, we're like, nope, no toast type def here. And then we pass the params, which is a list of string. And basically, we loop over. Yeah, we try to parser, wait, consume whitespace and parser dot consume name, which is lowercase. And if that doesn't work anymore, like param, then we break. Or break. And here we have params dot push this. Okay, so down here we have saved all of the params, and we can, yeah, we then expect an equal sign. Yeah. Is there like a, I mean, we can consume, wait, we did that because we did a break out of the loop. So before that we consume whitespace. So we can just check parser.current unwrap unexpected input and after type def name and params, or horrible name, but horrible error, but okay. Yeah. Yeah, this should be an equal sign, or we panic, expected flip after type, let's call it type signature. Okay, advance, wait, consume the equal sign, and then we basically want to either pass a type right there, or make sure that we have one child, which is like the content, which is the type. So this will actually be pretty similar to this, I think. Yeah. So if the bacon children is empty, then we just want to parse, yeah, a single type expression. And then we want to be at the end of the input. Beautiful. Otherwise, we want not this, but yeah, we also want to be at the end. Yeah. Yeah, the question is basically what is the type? If we don't have any children, we pass type, make sure that we are at the end of the input, and then we evaluate to the type. Yeah, otherwise we consume whitespace, make sure that we are at the end, and then we ensure that bacon.children dot equals dot len equals 1, type def, but types given. Yeah, I don't know. Weirdly formulated, but so then we say children get please get the only child and convert that to a toast type. Okay, so then we have a type, and then we can create a toast type def. Yeah, and the toast type def, I think it didn't have a name, it had params, which is our params converted to a slice. It had the type. Actually, I think that's it. Right, the toast type def, yeah, params, slice of string, and a type. Sure. Okay, so now this should work. There are no definitions named parse type def. Is it called to type def? Because this is, oh wait. No, just do this. Bacon to type def. We work on a higher abstraction level than parsers here. So there are no definitions named to type def. What about to toast type def? I guess that's sure. To toast fun def. Yeah. But first let's fix the errors up here. So consume name, no, this is parse name, sorry. Parser.advance doesn't work because this parser is created in the scope and it has to be mutable. Okay, what's in here? Expression is something. Let's just, I don't know what's that. Okay, then for to toast type of bacon with the variants. Yeah, for each of the variant of the bacon children we do stuff. And yeah, okay, I guess same thing here. We need to add error handling to this parsing. You can't just say, well, it doesn't work, here is some random data state, you know. Previous, okay, default case, which is the else. Yeah, I need to fix the error messages. Yeah, this evaluates to a toast type, but previous case to a bool. Right, because this should evaluate to the type. To toast type. Yeah. Yeah. Okay. Yeah, to toast fun def. That's cool. Okay, to toast fun def. And let's just say this returns a maybe toast fun def. Like this. And there's just a to do in here. And a fun def, but we can actually like implement this. Because here we push the definition, or something like that, you know, toast def dot type to the definitions. And here that's just the fun. Toast def is not an enum type. Right. Toast def is not an enum type because yes. Yes, the name is basically ignored, right? Yeah, that's weird. Show if the parsing. The to toast type. I mean, yeah, that makes sense. To toast types. To toast type def. toast type def, but this name thingy is not even used. It just gets discarded. So this should just be a toast def. Yeah, I know. And then down here we create, sorry. Oh, yeah. Toast, we create a toast def with a name, and the kind is toast def kind dot type of this. Toast def kind dot type. I thought usually it says which kind of variants it supports. Toast type def. Oh no, toast def kind dot type. We don't need an underscore there. Oh, toast type def. No, hang on. Def. Yeah, we can just do this. Okay, yeah. To toast fun def. Oh, right. This needs to take a bacon. Sure. Oh, now we can even like clean this up. Look at this. Beautiful. Beautiful. Concise code. True. This call doesn't work. Okay. Because we try to write a toast type and we can't do that yet. That is true. So let's fix that. Let's write a toast type. I mean, basically, we just switch over the type. You know, if it's a variable, we just write that variable. If it's a call, call name, and then for arg and call args, space, and then the arg. Yeah. And if it's an enum, well, we just write a pipe, and then for variant in enum, oh, yeah, I mean this, we can just say, let's write the variant name, maybe like this, and then for each arg in variant.args, do writer dot, rewrite the argument, space separated, and then a closing parenthesis. Doesn't have args, true, it has values, and that's a slice of stuff. Okay, yeah, def, this is not a variant. True, there are no, oh, there is var though, so, oh, like this. Yeah. So I'm gonna toast and int switch condition. Oh no. Yeah, this should be a toast. A value similar to these. actually, let's check the toast var. Okay, only a name and toast value, that makes sense. Okay, so this call doesn't work. Writer, slice of toast. Slice of toast values. Yeah. I guess. I mean, value is kind of. Let's rename this to expression. Yeah. Sure. Yeah. Okay. Okay. Cool. 100. Oh, this is the egg. That's pretty cool. Only contains these fields, defs. True. Yeah, so in the egg we need to do stuff. But for now, let's actually not do that. Let's just say we ignore all of that. We just want to focus on the parsing first. Oh. What? Okay, so we have the bacon. Seems it should. Expected type expression, right. And enums cannot be specified inline like they are here. Instead, you have to do multiline things. And let's do that. You should be able to do something like this. Yeah. Expected type expression. Well, I mean, we don't know where. Let's maybe remove this and check if that works. Okay, additional garbage online, true stuff. Oh, we have so many places where this is the error. I mean, we kind of have this right here. If children is empty, that's not the case. Then we just make sure that we are at the end. Convert those to toast types. Okay, you know what? Let's start small. Okay, handle fun def. That's true. Sure. Okay, yeah, we don't do that yet. But that's fine. Okay, so this should somehow get handle fun def right here. Let's actually do this and just ignore stuff otherwise. Whoa. Okay, so this gets passed to an enum with two variants, true and false. Nice. And now how about true int? Oh, I think I know what the error was. Whoa, look at this. It's a true variant with an int and a false variant. And we can put multiple of those here, like this. And we can also split things across lines. What? Nice. That's pretty cool. Yeah, before it didn't work because we don't support parentheses. So this doesn't work. Yeah. There is a way to fix that. Pretty easy actually. So when we parse type atom, yeah, we basically want to check is the current, you know, if parser dot current or return non-toast type, yeah, if that is an opening parenthesis, then we want to consume that, and then we want to parse a type expression. Because now inside of the parentheses we can use spaces, that's allowed. And then again we need to check that the next character is closing parenthesis, expected closing parenthesis, and maybe some more like, you know, consume white space in here. Okay, so this call doesn't work because yeah, because it should be like this. Similarly here. Okay. True. So this doesn't evaluate to nothing. What we want is, yeah, to just return the type immediately. Yeah. Expected type expression. Well, you know. Okay, parse type atom. Wait, parse expression doesn't even call parse atom. Why doesn't it? Oh, it does here. Yeah, I think it, like, still it should just call parse type atom. Yeah. If, sorry, parser parse type atom. Additional garbage, what? Okay, so let's maybe go at this from the other way, from the like top level down. We parse a type definition, sure, with one child, so there shouldn't be anything on the same line, and then we say, hey child, please turn yourself to a toast type. And this will then look, okay, I'm just a pipe. So I'm going to look at the variants, meaning you know, I'll have a parser and I parse this symbol. The children are not empty. Oh yeah, they, you know, yeah, this line doesn't have any children, so the children are empty. So then after, you know, parsing the initial symbol, the true, we then consume white space and parse a type atom, including parentheses, what we just added. Yeah, that should work. Why doesn't it work? Cursor, pause, input len. Input len. Oh, we don't consume the closing parentheses, maybe? Because it's almost at the end with like parsing. Yeah. That's exactly what's happening. Yeah, I think we need like a consume function or something that makes this. Oh, look at this. Ooh. Nope. I think there's not an error in the. There's just an error in printing. Yeah. Just always add. Oh, sorry. Always add parentheses around calls. Beautiful, I guess. Yeah. Okay, so this is either true with these things, or it's false. Nice. We can pass types. Ugh. Cool. Okay, I guess first step done. Next would be parsing functions. Okay. Parsing functions. Let's add our test function, which we had at some point, yeah, this right here. And let's actually, yeah, okay, it doesn't get parsed right now. But we want to parse that. So we try to turn it into a toast fun def. Yes, otherwise we panic. I couldn't parse line bacon dot line. Handle fun def, indeed. What if we just return none? Then it should say, well, I can't pass this line. Yes, couldn't pass. Wait. This should get parsed. Oh. Oh, I see. Yeah, if this is a type definition, then of course we push that, and then we just continue on to the next child. Well. Okay, couldn't parse line. Yeah, this is better. Couldn't pass line main, and then an input, and int a bool. Okay, so let's look at that. Yeah, this right here. To toast fun def. Basically, you know, we had some code for parsing expressions right here. Yeah, when we say like create def and stuff like that. Yeah. Okay, so we can simplify this later on, I think. Okay, so parsing a function. Let's just go from this, like from a greenfield perspective, like we don't have any code written yet. How would we do this? Well, first we want to pass the name. So, oh, hang on, yeah, we need to create a parser first of all. And I think for now let's just say that the entire signature has to be on a single line. Yeah, in the future it makes sense to, oh, I don't even know how that would look. Something like this, perhaps, or this? Oh. No, I don't know. For now, let's just say function signatures have to be on a single line. Okay, so we create a parser. First step. Then we want a function name. Parser dot parse name, and this only passes like lowercase names. Yeah, if it doesn't work, then we just return nope, no function definition to be found here. And remember, like in the top level, you can only define functions. We could even like think about disallowing constants, maybe. Well, I'm not sure about that. We'll get to that later. Okay, so we have like we want constants to be defined top level. That should work, but maybe not at this stage. Well, we'll see later on. Okay, so we have a name, sure. Then we consume white space, this one right here. Oh, well, actually, now we want to be able to parse like multiple. No, we want to be able to define this. A int, B int produces an int, and then something inside. We want to be able to parse this. So basically, we need a loop for the arguments. The arguments are just a list of what's it called, toast, param, stuff like this. Yeah. And then we consume white space. We consume the argument name, so parser dot parse name, which should also like be a lowercase thingy. Parse name is not okay. Never mind. Yeah. Then we parse a colon. Parser dot hate that. Okay, we'll need, after this we'll do some refactoring of the parsing, and I'll add a consume function for consuming a single character. So after function name is after param name. Yeah, we expect a colon, or we expect flip after param. Okay. Then we have a colon, then we consume white space. And then we want to parse a type atom. It can't be like something like this, you know, or like even a list of it. It has to be an atom. So parser dot consume type atom, or panic expected param type. Consumed, oh right, because it's called parse type atom. Expected param type, nice. And yeah, we basically just add that to the params list. So params dot push toast param with a name and a type. And oh, this is a maybe something, or break. Yeah, if there is no, you know, if at some point we're like, okay, we parsed an atom, now we want to pass the next parameter to the function. Oh, there is no name here. Well, what do we do in that case? We just, you know, we break out of the loop. We're done parsing parameters. And then we, after name, yeah, sure. So then what do we do? Then we want to basically consume, oh, how I hate this. Yeah, we basically want to consume the arrow. Expected this has to be a minus, or we panic. And I mean, you can see how this is ridiculous. This is honestly ridiculous. Okay, so we have a minus sign and then we have a larger sign. So now we have the arrow. Then what do we do? Then we want to pass another type. So consume white space, pass type. Okay, consume white space. Type is pass type atom. Yeah, expected return type is what we want. Okay. Yeah, let's call that return type. And then we want an equal sign. So parser consume white space, parser dot, oh, come on. Okay, expected an equal sign. Okay, so then consume the equal sign. And then what? I think then we want to well, there are two ways this can go. Either we have children, in which case they are the body, or we don't have children, in which case we want to pass the rest of the line. You know, either we have this with an indented body, or we just want the rest of the line to be the body. So if bacon.children is empty, then we do stuff, otherwise we do other stuff. So if we don't have any children, then we want to pass an expression on the rest of the on the parser. Let me just see. We have something like parse. Yeah, parse expression. Sure. Parser.parse expression. Parse expression, then we want to consume white space. We want to ensure that the parser is at the end, like this. Yeah. Then we want to evaluate to the body. Otherwise, if we do have children, then we basically want to do whatever we did down here. I don't know where that is. Yeah, like a toast body of the children. Yeah, we want to do this. So pass the children into toast expressions, and then the body is this. we evaluate to a toast body of those children. Okay, so this is a toast expression. Okay, yeah, and then we just return, we are done, we have toast definition with a name, like every definition. Yeah, and the kind is toast def kind dot fun, and it contains a toast fun, which again contains params and return type and a body. Okay. Yeah. Nice. Whew. Yeah. Okay. Now we go into the like expression things. Yeah. All of this should be like toast. Actually, like most of them. Let's actually. Now let's say we replace all of the toast with toast expression, because in most cases this would be correct, except for the top level things, you know, except for these. They should just be, you know, like here writing, as it, yeah, writing a top level toast. We want to be able to do that. And down here we want the main thingy to result in a toast instead of a toast expression. Okay, so 2, 3, 1. Yeah, here we create a toast def. Oh yeah, this is not a toast def. Oh, where is that created? Down here, somewhere else. Yeah, here, but that's fine. Yeah, so inside of, you know, we turn something into a toast expression, so we're inside of a body. And here we don't want this fancy, like, okay, this is a switch, sure. Then we pass an expression, which may be something complicated. And then we say is the next character an equal sign? If so, then we advance the cursor and we call this create def. That create def then looks at the expression and it checks, is that a name? Then I just want to create a variable. If that's a call, that's disallowed actually, because inside of functions you can't define other functions like this. So yeah, I mean this is just, you know, this looks like a call, and it definitely is a call, because functions, they need types for parameters. They look completely different than this. We may allow at some point, you know, we may allow closures like this. I don't know how that will look, but basically something that accepts an A and a B and it returns, I don't know, something like this. And then you can treat this like a first class function. Sure, we may have that at some point, but yeah, for now, nope. Right, so this is a name. Yeah, create def. And this defines not a def but a var. Yeah. definitions can only, variables can only have a name on the left side. And we call this create var. Beautiful. And you know, in the future we may add pattern matching and stuff in here as well, but for now. Okay, so parse expression, what does that do? Well, it just says this is a var. Sure. Down here, I don't even know what to make of this, but sure. To toast express, we have this, add this, expression push, make and do to toast. We have a list of toast expression, we have a toast. Oh no, to toast express. That's what we want to call. To toast expos. Yes. But actually this can't happen. Yeah. Is there some error inside of here? Yes. Okay. Okay. Yeah. Maybe. Well, this is maybe. Expected function body, you know. Like if you write something like this, that's an error. If there are no children and there is nothing after the signature, after the equal sign, that's invalid. Okay. List to slice. Okay, so yeah, params is params dot to slice. Beautiful. Okay, I can work with that. Wow, it compiles. Right. Okay, so wait, let me look at the I mean, sure, minus can be an identifier character, and that means that minus can also be the name of a variable. I guess that is true. Do we want to allow, you know, writing a function like this? You know, so that minus is also a name. I think not, actually. No, I think that, and also for like normal variables and stuff like that. I think, and even in, you know, if you have generic types like list of t, we don't want you to be able to do this. So we need a separate notion. You know, we have symbols, which are uppercase. We have names, which are currently like anything that is not uppercase. So this is a symbol, you know, and you can use this as a parameter name and a function name and stuff. But I think we need another concept. We need basically like a lowercase simple thingy like input. And then for function names, we want to allow either symbols or lowercase names that would be similar to how it works in Martinaise. So this can either be like a lowercase string where the first letter is lowercase and then just characters and like letters and numbers and underscore, or you can have symbols, but then you can only have symbols in the name. I mean, I like that in theory you could also use like a kebab case here, that you could say list of int, you know, and this is like a valid variable name. I kind of like that. Yeah. Let's just say that you just can't use this arrow as an identifier. You know? We advance stuff, and then if start is end, we say, well, nope, that didn't work. And if the identifier is this, and if the identifier is this, then we also say nope. Otherwise, we just return it. Okay. Interesting. Why? So we have a name. Sure, this works. And then this returns none. That's... Oh, right. Yeah, we also need to allow these in order for both to be passed. Okay, expected this. Sure. Yeah, maybe pass or like consume white space before that. I don't know. Nope. Expected this. A. Oh, horrible. This is the nice debugging. B. Okay. So there is a character, but it's not. It's not a minus sign. Found parser card. So I. Sorry, what? What the hell? What? Cursor's 19. Here. Wait, why are we there already? Identifier. I see. Yeah, we advance the cursor, but then we reject the thing. So here we need to reset the cursor. Yeah, parser dot cursor, we need to reset that to the start. Okay. Oh wow, this got parsed. Nice. We have toast. I mean, it looks horrible, but at least something. Yeah, all of the definitions, they should be separated by new lines. So let's do the usual dance of, like, you know, if this is the first, then set first to false. Otherwise, print a new line so that we have new lines between all of the entries. Okay, so we have this, we have toasts, and we have a definition, a type definition of bool. We have a definition of plus with an A, which takes an int, and a B, which takes an int, and it produces an int. Beautiful. And then the body, which is 2. And then main with a parameter list of int, accepting a list of int, producing a bool. Great. That's actually pretty cool. Pretty cool. Yeah. Okay. What else? Let's yeah, let's fix the indentation. That should be really quick. Indentation 1 for the body. Yeah, so this looks nice. Okay, that's actually super cool. And now yeah, I think let's refactor the code. I think I like that. Let's refactor the parsing code because there are so many, like, first let's commit it and then let's refactor that. Yeah. Sure. Yeah. Add support types. Support parsing types. And then refactor the parser. So there are multiple things I wanna do. So we have the writing of the toast, which is fine, I think. Then we have I just want to give this file like a general structure, you know. Parsing, like in this file, parsing refers to converting a single line of code into something toasty. Yeah. Yeah, I don't know. Something like this. And you can get the current character, you can advance the cursor, the parser, you can consume white space, you can, that's basically it. But what I want is to be able to say consume this thing, please, consume this prefix string. And it just tells me, did it work, did it not work? So basically I want to, you know, like start is the parser cursor, yeah, and then yeah, for each character in prefix.chars. I want to check that this is the character of the parser. Right, so check the current character. If there is none, you know, just maybe it also works. Or if that doesn't work, then just reset the cursor to the start and return none. Yeah, then make sure that this is the expected character, this is the actual. Then we make sure that the actual character is the expected character, or again we reset the cursor and return did work. And yeah, but of course we return false here until we return true, because then it did work. Right, so we can basically consume a prefix string, which is nice. Can we, I think we can even simplify this further, like consume, oh, yeah, we also need a parser. Yeah, we can consume a char. That's basically this right here. Yeah. We say what's, you know, the current thing. If that didn't work, we return false. If there is, if the parser is at the end, and then we ensure that those are the same, or we return false. Then we advance it, and then finally we return true. And then we can actually use that in here. We can say parser.consume the expected character, and if that doesn't work, we just do this. But then we have both of those simple, like unified into one case. Plus we can also remove those parentheses. Okay, so we can say consume a character and consume a prefix. What I also want is just a getter, you know, is at end on a parser, returns a bool, and that is very simple. It just checks. Maybe put that up here because it seems like very fundamental. It just says parser.cursor equals parser.input.length. Okay, so now let's like simplify the code. I think this is actually fine. Digit. Yeah. Parsing a string is also fine. If we look at the current character, yeah, that must be this. Actually, let's we can simplify that. We can say parser current has to be some of this. Ooh, do we also want to parser dot? Yeah, okay, yeah. We look at the current character, that has to be this. Otherwise, we return there is no string. Then we advance. Then, ooh, wait, even simpler. Parser dot consume this, or we return didn't work. Yeah, yeah, look at this. Nice. We save the start of the content, and then we say parser dot yeah, sure. Yeah, that looks fine. Parse name, sure. Yeah. I mean, white space. Basically, breakfast is only white space sensitive at the beginning of lines. And all of that was passed in the bacon. The rest of the code is not white space sensitive. You can, like, wherever you put one space, you can also put two spaces in there. So I think it makes sense to actually consume white space when parsing an int, parsing a string. You know, in these fundamental things, when consuming identify not really, because we can also just do that here. Okay. We do that in, you know, like consume prefix. Yeah, sure, why not? Why not do that here? Oh, yeah, maybe not here, I guess. Sure. Okay, but then we can basically just say, yeah, this is fine. We don't need this, I think. What do we even do here? We check, is this, oh, is the next thing an equal sign? I mean, like, this is just as a current. Yeah. You know what, let's actually adjust this to return a character. Yeah, and if that doesn't work, then it just returns the null character. Like, how does that work? Like 0 to byte, I think, or to char. Something like this. To byte, no. To byte doesn't work. What? Does this work? Okay, hang on. How do strings work? Martinaise, standard lib, string. Here. You can say to char on a byte. Okay. That's what I thought. Oh, I see. On int there is a lower byte. Yeah, you can convert that to a character. Sure. But then this just returns a char unconditionally. And this, you know, a null byte is basically, it matches no parser. That's the idea. So then you can just say, is this white space a break? You can just say, yeah, you don't need this. You can just parser dot current equals char, or return false. Nice. Nice. Yeah, when you want to consume a string. Yeah, I think I want to inline whitespace, like consuming whitespace in here. But I do want this to only match this prefix and not match anything if, you know, basically if the if there was white space in between some of these. So I can't use consume of the characters, but instead I'm just going to inline this. Yeah, let me check that. Current.char. Yeah, or we do this. And then we advance. Yeah, that's fine. Okay, when parsing an integer, we look at the current thing. Don't need some or something. You know, similarly for a string, we can just say, oh yeah, consume this character, which automatically consumes whitespace before that. And then we just say, well, what's the current character? Yeah, this doesn't exist basically, but we need to handle that. So if parser dot is at end. And the reason we need to handle that in strings, like parsing strings specifically, is because strings can consume any amount of input. They consume like they don't care what they consume, and that makes string parsers different from all other parsers. Well, my camera just went off. Okay, so then we get the current character if that's... Oh, we can simplify this. If parser.consume this, then break. Nope, not nice, but we can check this. Yeah. Okay, then we advance. Nice. And then we have identifiers, where we basically just check some stuff. I mean, you know, it doesn't hurt. Okay, so parsing a name will just, well, yeah, we'll do exactly this. We look at the current character. If that is not uppercase, then we return. Nice. Yeah, similarly here, all of those get parsed. Sure. Parsing an expression. Now things get interesting. So expression is parser.parseAtom. Yeah, and this is where we got stuck before. So here we can basically say, just say, well, this should be an equal sign. Boom. Oh, sorry, we can do this, and we don't even need this. You know, if we consume an equal sign, then we advance the parser even further. Well, that's not quite correct anymore, but I see. Yeah, just pass an expression if that works, stuff. Otherwise, this might. Okay. Then parsing a type atom. That basically just checks is can we consume an opening parenthesis? So much shorter. Then we pass a type parameter. Then we need to make sure that the next character is a closing brace. So parser.consume closing brace. I mean, this almost reads like a high-level description, you know? We consume an opening parenthesis, so then we pass a type. We consume the closing brace, and then we return something. Nice. No. Okay. Okay. Pretty cool. So then here we create a parser. We do that in some places, you know, so let's create a constructor for that. Yeah, really, this just creates a parser with the input and a cursor. Oh, true. No, nice. Parser.current. Nice. And then we advance. Well, this is just a consume equals sign a panic. Right, but where were we? Up here, somewhere. Yeah. Right, when creating a parser, we can just say, well, I want a new parser with a variant per line, like this. We pass a symbol, we say, are the children empty? If so, you know, we pass these, so we can just inline that in here and inline that, and look at how things become more and more compact. So then we consume white space and we make sure that it's at the end of the line. And this is like a very common pattern. Same down here. So let's actually add another getter for that. We already have is at end. Let's have a is done parser, which calls parser.consume white space and then returns parser is at end. Yeah. So then in here we can just check parser.is parser.is done or panic. This doesn't work. Is done parser. Alright, this is mutable. True. Yeah, same here. Okay. It's actually kind of concise now. Okay, in this case, we also create a new parser. And then we pass a type. And that should be everything in that line. In this case, we pass a name. Then we should be done. Nice. And then yeah, this looks fine. Here we can create a new parser like this. We say we pass a symbol, sure. Here we push, we don't need this. Yeah, so we don't need these. Yeah, right, we consume these, we pass a type expression and we make sure that the parser is done after that. Here we just make sure that it's done. Okay. Again, we create parser, pass an expression, make sure the parser is done. Similarly here, create parser, pass a symbol, push things to the params, expect a colon, so consume a colon or expected colon. Don't need these probably. Yeah, because in here we just do this. We say parser is done. Yeah. Okay. Okay. Ooh. Ooh. Okay. Parser input get, I mean this is just the current thing, but we can also directly say consume an equal sign please. We don't need this. So if we consume an equal sign, we set the expression to this, otherwise to this down here. And then we say parser is done. or that's an error. Yeah, not needed. This, not needed. This will just consume this. Yeah. Yeah, this is just parser to consume the error. Okay. Yeah. Cool. Very, very cool. Yeah. Let me fix my camera. Okay. My camera works again. Right. Yeah, I think let's just test this and see if it still works, and it doesn't. Well, parser has to be mutable. 300, but we also have an error here. And up here. And down here. But the code has gotten so much more concise. Like so much more concise. Okay, let's just commit that. Yeah, we can see that. I mean, look at this. that's just crazy. Instead of being, well, consume white space all over the place, even though like we basically allow white space anywhere. Like anywhere between names and like stuff. Yeah, and checking if the current thing is a colon and then advancing and having to unwrap things and stuff like that. That's all of that got simplified into, well, consume a colon or panic, expected a colon, consume an error or panic, expected an error. Okay. I mean, we can even like have an expect something, but let's not do that because I think later on we will have more. We won't just panic. We will have like proper errors and stuff like that. And we may want to attach more information to those errors. Okay, so yeah, this is just refactoring, refactor parser, refactor parsing. Sure. Yeah. Cool. Cool. What's the current state? We have this toast with definitions, which are either type definitions or function definitions. Now, the next step would be converting that to an expression graph. So basically taking this thing that like roughly corresponds to the syntax of the file into something that that is more like, that only contains the semantics and is a lot more lower level. So the expression guided graph, the way we do that currently is that we yeah, we have this function to egg on a toast, and it does some things. But we see that this already takes an egg body compiler, because even though initially, now we have these different kind of contexts in toast. We have the global toast, and then we have type definitions, and inside of them there are only types and stuff like that. And we have functions, and inside of those are expressions. Before we didn't have that. Before we just had one toast expression, and everything was treated the same. But then in the egg, we actually treated them differently. We wanted to have top level things that behave differently in things that behave different in the top level and the non-top level, basically. Now we don't need to handle that anymore. We just say we want a toast, sure, boom. And then we just say for each definition, and toast.defs, please do some stuff. And yeah, exactly, we can just define the definition name with things. Okay, let's actually look through this, because I haven't really done that. Okay, so we have the definitions, which are egg definitions. Fine. Then we have these types. We have these tracking which functions basically are visible. Functions and types, I think. Yeah. And then, okay, we put all of the built-ins into scope. Sure. Yeah. I mean, we may have to change this actually, but we're gonna do that later. And then all of the definitions that are defined top level then immediately go into scope, because they are unordered. You can access a definition that is way down in a file. You can access that from the top. So yeah, then for each of the toast defs, we know it's a def, sure, we can take the name, I guess. We can take the value, okay. And this is either a fun or default. Now everything is fun, even if you define, oh, can you actually do that? I think you can. You can define a foo. Ooh, you would have to do it like this, right? I mean, that's super awkward, and we will probably change that, I think. But yeah, if you don't have any, there are no global constants right now. There are only functions with 0 parameters, basically. And I think that's actually fine, because inside of this, you may actually, I don't know, just panic, for example, or do some debug printing, which works. So there may be some of these very limited side effects happening inside code, inside any code. And yeah, if inside of a function you access foo, I think only then should the panic or the debug printing be executed, not just automatically just because foo is defined somewhere. But that also means that it needs to be executed each time that foo is used, I guess. Or we have the first time it's accessed and something, but then again it's inconsistent, and that's kind of weird. So I think let's just go with it's like a function call to a function that accepts 0 arguments. Okay, so yeah, with that out of the way, let's simplify this again, and let's look into the egg. So yeah, we check the value. We don't need that at all. Yeah, we can say, what do we do here? Inside of the definitions, we put this. So I think in the egg we actually want like separate scopes, maybe let's call them, for function definitions and value definition, function definitions and type definitions. So I think it makes sense to have, you know, not, basically I just said that values no longer exist as a separate concept, they are just normal functions, although with 0 arguments. And built-ins, I mean, sure. Yeah, I guess that they are here. Mm-hmm. Expression. Yeah. The question is, how do we bring types into this? That's basically the challenge. And I think, sure, we can have like types as like a separate concept up here. You know, we have some way of representing types in the egg. That seems fair, I think. Yeah, but the question is, how do these interact? How do we do we attach types to these egg functions? Maybe. Maybe we do. How do these egg funs get created? I wonder. Okay, there's an egg body builder, which contains an egg fun builder. Okay, and then I see. Yeah, so that's maybe, I think it makes sense to say that we only have egg funs. And ooh. You know, like even built-in functions, they have parameters. And they should be type checked, I think. How do we do that? You know, like yeah, basically when I have a function, the function also has like some like the body of the function. Okay, I get that this can either be an egg body or it can be a built-in like this. But the function itself also has like some external things. It has a signature, like you know, the parameters, for example. It has yeah, parameters which are just the types, I think. A slice of egg types. It has a return type, which is an egg type, and it has a body. And even like built-in functions, before built-in functions didn't even have this, basically. Built-ins were not really egg funs, they were something else. And they were type checked later on. But now we also want to have information about like what parameters do they accept, what's the return value. Like all of this type checking and function resolution and overloading and stuff like that, that should work the same regardless of whether something is a user-defined function or a built-in. So I think it makes sense to have these basically up here and then have the basically the implementation. I like that, the implementation as an egg fun apple, and is either implemented using a body or it's built in. And I think the body actually has to yeah, it's like an egg fun body, I guess. Egg code, maybe even, you know, just some egg source code basically. Yeah, it's either implemented with code, normal, you know, code, or it's built in. And the code, you know, it's a list of expressions and it has like this body, and the body can then reference parameters, those that are where the types are declared up here. And, you know, all of that, but that's like an implementation detail. That's only how the function is implemented. Yeah. I think that makes sense. First to egg type, but that type doesn't exist. True, we don't have types yet. Yeah, that's like another thing we need. So what's an egg type? And remember, these are like types where we need to like match them and stuff like that. Oh, that doesn't make sense to like kind of call types, you know, call type definitions while we're converting something to the egg. Maybe. So basically my idea is that if you have a function, I don't know, not, which takes an A, which is a bool, and it returns another bool with some content, and you have a function and, which takes an A bool and a B bool, and it returns some bool, I don't know, then in the egg, you know, something like bool doesn't even need to exist. We don't have named types anymore because our language has structural typing, so this will basically be converted into this. We have A, which is like true or false. We have B, which is, you know, true or false. Those are just enums. Yeah, I kind of build it like this, but you get the idea. So basically we have this already, and if you have another example, like a list getter or something, a list of T, yeah, like a list of T, and an index int returns T is implemented in some way, you know, that this will actually be like, I don't know, list is probably defined as, well, I don't know, like later on it will maybe just be like a struct with a buffer T, and buffer being like a built-in type. I think that we need some way of representing like growable memory or something in the language. I think, at least. Yeah. And length, which is an int. And then you can, yeah, but for now we'll just do something like this, because this is equivalent to that from an, again, information theoretical perspective. And yeah, so this will basically just be converted into get list, where this is, you know, an enum of list of buffer t and int and an index, which is, yeah, like this. So here you don't have these named types anymore, these type aliases, but everything gets resolved into like fundamental things like enums and type variables, sure, and like built-in types. But that's the only thing you have. You only have built-in types like buffer and int and enums, and you don't have these named type aliases anymore. These are already resolved. Because then in the next step, because I'm just anticipating what the next step will be. The next step will be like actually compiling function bodies and resolving types and stuff like that. And then, you know, if you know a get function is called with, I don't know, you create a list, for example, and that returns you something of the type list of int, which is just basically another way of writing this up here. So it's a list of buffer int and int, an enum of that. Now you have a list of this type, which is something of this type, and then you call something like list get 0. We want overloading to work, so we need to check for all the get functions which function matches these argument types. You know, we have something of this type and we have an int. And that is much easier when all of these are already normalized into these like structural representations of the type, rather than saving, well, this is a list, and then you need to look up what was list each time that it's used. Yeah, so that's basically my thinking behind we want to save resolved types, which are only like types that only have a structure. They don't have names anymore. Which is the entire idea behind structural typing. So yeah, that's just, yeah, these calls that don't exist. So this can be a variable, sure, we can still have type variables. And in fact, you know, we basically, when we execute this get call, we want to check, you know, we know these are the arguments that we give to the call. Then what are the parameters of possibly matching functions? And we have this one function with these, with this signature. So then we can like structurally match those. And we see, okay, this matches, okay, then t has to be int. Okay, so the return type of that is int. So basically, in order for this matching to be efficient, we want those structural types to basically be only structural, not named. So we don't have calls anymore. Yeah, but we only have variables. We have built-in types, which we need to now specify here already. So for example, int is an egg type, which is like automatically in scope. And oh yeah, this is an enum, of course. Yeah, or we have an enum with strings and slices and so on. Cool. Cool. Yeah. Yeah, I should also like document things up here. The syntactical language construct. This data structure roughly should correspond 1-to-1. Well, should roughly correspond to the content of request files and be suitable for formatting, etc. Yeah, that's the basic idea. Just represent the source code as it is. And I mean, we even violate this in some places. Yeah, this is a slice, okay, that's fine. But there were some cases, yeah, an enum is a map. I think in the long term it would make sense to have like a vector, a list of enum variants, because we don't want to reorder them, for example, when formatting code. Right, so that's the basic idea. Just represent the source code. This is represent only the meaning of the source code, but don't like have any sort of type resolving yet. Yeah, a graph with resolved types. Resolved variable types. Let's call it that. Ooh. Yeah. Some of the function calls, they are not resolved yet. And in fact, no, all function calls are not resolved yet. Because in here we don't do like, specialization, monomorphization of functions and overloading and matching types and stuff like that. A graph where names of local variables are and where names of types and local variables are resolved. Function calls are not yet resolved as resolved. Yeah, maybe separate that. Types. A graph names of types are resolved. Nice. Yeah, calls usages of type definitions, which are more like aliases anyway, have been resolved so that types have no names anymore. They only contain their structural. They are completely structural. Yeah, something like this. And yeah, we don't have this. A representation of code that is more suitable to resolving types and doing fancy stuff later on. Types, yeah, functions, names of locals and types are resolved. Function calls are not resolved to specific functions yet, as this requires overloading resolution. Cool. Nested expressions in function bodies have been flattened out, have been flattened to a series of small yeah, this, I think this kind of describes what this stage does. Okay, so yeah, this makes sense for now. Wait, we do have strings, right? Yeah, so we'll have string as another type in here. Okay, so egg fun. Okay, yeah, those, like, we have to refactor a lot of this. A lot of this. Hey, I mean, we don't have types, that's cool, actually. Yeah. More suitable to type checking. That is simplified, and more suitable for type checking. Yeah. Yeah, cool. Okay. Now let's look at this egg call. Yeah, we kind of need to. Nope. Nobody. This will just be a string. We don't know what function is called yet. Yeah. And we can't, if we don't reference global functions, like as expressions, you know, we can only call them. And oh yeah, that actually makes, like, from a language design perspective, what we don't want to be able to do something like this, you know. Because there may be like multiple get methods defined globally, and we don't know which one to choose. So I think just using global functions like this is not supported. You have, like, I know at some point we will have functions and like closures, but at that point I think you will have to basically create your own. I don't know how it will look, like this is more like a Rust syntax or something. But basically you have to create a typed thing so that you can then call a global function that still works. You can wrap that. And again, we may even lift some of those restrictions later on. But for now, like no function pointer getting or something like that. No. Okay, so an expression can either be an int, it can be a string, it can be a symbol, it can be a switch, it can be a call. Nice, I like that. yes, this, like all of this still seems super valid. Yeah, let's actually remove this for now. And we may add that later on if if we want to display error messages. We don't just want to have the full structural definitions. Say, well, it expects an enum that looks like this giant thing. We may want to like substitute. We don't want to substitute a list of int with an enum with one variant with a buffer and a len and stuff like that. No. Yeah, but that's later. For now, everything will just be completely structural. Okay, so we have an egg, and for each of the funs, because these are only functions, for each of the funs, yeah, we basically write down the function t. What? No. This is just a list of functions, yeah, because there can be functions that have the same name. So yeah, you need to support that. Cool. Okay, yeah, let's actually so we have functions, and then we say we want the name, we want to print that, and then we can print the types that the function accepts. So for parent in fun.params, we basically want to print a space. Okay, yeah, it doesn't have a name really. Well, yeah, but we can print the type. It is just a type, right? Yeah, it is. Okay, just this, and then we write the return type, which is fun.return type. And then we have an impl. How the function is implemented. Yeah, basically we want to say equals sign, and then switching on the impl, the values don't exist. If it's like normal user code, then this is an egg code body. Yeah, sure. Okay, and then we have function. I think we just want code in here. Yeah, we don't need the entire function. Nice. With a notation of 1. If it's a built-in, then we just omit that like this, because why not? Okay, now we are getting somewhere. An egg ID, and let's just replace that with add, because I think that's consistent with how it looks in the yogurt stage. So we have a body, we have not a fun, but code, which is egg code, which is actually, I like the distinction between, we have a function which has a signature and can be inspected and has a name and stuff like that, and then inside of that is the code. So we want to print an egg body with code, which means we print the parameters. Sure, those are just egg IDs, I think. And then for each of the IDs inside of that, reprint the ID and then the thing inside of that. And to print an expression using some code, we can yeah, basically do this. And for calls, it's a bit weird. The receiver is a string, I think. Yeah, and then we have arguments. Yeah, nice. That should work. Variable scoping. So there is name binding, and there aren't really like global names, I think. So let's just not do that. And instead, actually, let's just map directly to an egg ID. Does that make sense? I think it does. Or maybe let's even rename this, like just have a list of name bindings, and a name binding has a name and an ID, because it binds the name to an expression. That makes sense. And then in here we just have a list of name bindings to define a string as an ID, like this, I think, maybe. Yeah, we basically I'm not sure how we do that. Well, yeah, I think let's just say, let's just continue with this, and we'll see in the end if this works out. Yeah, we do this if binding dot name, then we do binding dot ID. Yes, makes sense. And then we have a snapshot. Sure, restoring that. Nice. Okay, converting a toast to egg. Yeah, so basically we want funds, and this should be not a list, but not a map, but a list of egg funds with visible things. And then for each of the built-ins, with this I mean built-in functions, we basically define a function named built-in underscore something. Oh, yeah, we don't really need that, because in this stage functions aren't even defined yet. Yeah, we may do this, you know, basically define a function with that name as a built-in function, sorry, as an egg function dot built-in. Oh, but this, like, this depends on the parameter types and return types and everything. So basically we need to create the signature for each of these built-in functions. Yeah, so the signature of a function is defined in egg types. Yeah, that makes sense, I think. But still, let's maybe create built-in fun with the built-in, and it returns an egg fun. I mean, an egg fun only needs a name, which is like built-in, then the built-in. It needs params, which is a list of a list of types, and return value, which is also a list of types. So maybe let's switch on the built-in. and always return basically a tuple of the parameters and the types basically. Yeah, so these are the builders. You know, if it's add, then we just want a list of eggtype.int, eggtype.int, and it returns eggtype.int. Yeah, that's the signature of the add function. By the way, similar for the subtract function, and the multiply function, and the divide function, and the compare function. Oh, not quite. It accepts an int and an int, but then it results in an enum, and an enum needs to have. Well, let's do it like this. Yeah, needs to have a map from string to type, probably. Yeah. Oh no, string to slice of stuff. Yeah, so it's either less to an empty slice of egg types, or it's equal, or it's greater. Sure. Then, wait, what other functions do we have? We have the concat function, which again is similar to the int functions, except it operates in strings. We have type info. Oh, this is cool. So type info. Let's maybe write down the type of the type info function. The type info is basically generic over a T, so it accepts. Oh no, wait. Yeah, okay. Let's say for now it. I think, you know, when I designed the language, basically had in mind that because of, you know, doing something like this, you may want to have types as first class values. And I think that makes sense. So let's actually do that. Let's say type info accepts a type, and it returns an enum that says, you know, it's either an int, or it's a string, or it's a type, or it's an enum with, you know, a map from string to a list of types, of types, yeah. Ooh, not even of type info, of types directly. And then if you know, only if you iterate into that and you call type info on that, then you get more information about that. Okay, so let's do that. Yeah, I think in the egg we need a new type. The type. Yeah, and then in here we can say, you know, the type info function, it accepts a single argument of the type. Let's copy this, because this will also be like an enum, and yeah, and then it returns an enum of either, you know, it's an int, or it's a string, or it's a type, or it's an enum, and you know, there should be some things in here, like a map or something. but we don't have maps yet and lists and stuff like that. So for now, I'm just gonna say this is just an enum. Okay. Right, we have int string type enum. I think that's it, but I can actually look up here if that's it. Int string type enum. Yeah, type variables don't exist because they are like monomorphized and like they disappear in the next compiler stage. Okay, yeah, that's the type info function. Crazy. And what other built-ins? Oh, crash. Oh, crash is interesting. So crash takes a string, the message, and it returns never. Do I need to? I think. Yeah, I think I already need never as a type here. Yeah. What? Okay. Yeah. And that's before this compiler stage was basically untyped, and now like all of that is just going in here. Yeah, and we want to get a compiler error if we add a new built-in, because then we need to add a signature. By the way, I really like this because now rather than, you know, when converting a built-in to yogurt, we don't need to check that, oh, is this really an int? You know, we need to cast it to an int, or we say, well, hey, you called this with a non-int. But instead, because we support overloading and type checking and so on, and built-ins are type checked the same way as other functions, if you call add with an int and a string, we will just highlight this as an error, like, hey, no function matches this signature and stuff like that. So yeah, we have this central definition of the signatures of the built-in functions, and then those just work automatically. Yeah. Okay. So here we have this. Params is the first element of the tuple, so signature.a, and the return type is the second element, signature.b. And it also has an implementation. The implementation is fun impl.builtin. You know, basically a later compiler stage will take care of this. Nice. But now, because we have this, we can up here just say built-in dot create built-in fun. Nice. Yeah. Then there was this for def and toast.funs do stuff. Yeah, no, we don't do this because functions are resolved later on. And we don't need this, we can just... Oh yeah, and this fun is the push because it's a list. Wow. Okay. Okay, that's kind of crazy. Okay, so we have all the built-in funs. Nice. Yeah, and then we have the other functions where we basically check what's the name, we snapshot the visible things because the local variables that are defined inside they are... Oh, wait. Visible only tracks local egg IDs. What does this you know, like snapshotting and restoring, so we can just, boom, create a new one. Oh, that is so elegant. Okay, so we have the name, which, I mean, let's be honest, we can just get that on demand, I think. We don't need to save that here. Yeah, and then we track which things are visible. We have the value. What's the value? Oh, yeah, that was when we had globals and functions, and both were kind of handled the same, but also not. No, don't need to sneeze. Or maybe. No. Yeah, so this basically doesn't exist. We can inline this. Yeah, I mean, the code just gets much more clean. We have the compiler, which is an egg fun compiler, sure. Then we create an egg body compiler. We say, hey, for each function parameter, please define this parameter name. Name, because in the toast we have egg param, which contains a name and a type, and we're only interested in defining the name, like putting the name into the visible thing. Then we have the body. Oh yeah. Oh, this is weird. Okay, yeah. Var returns. Yeah, that's the fun body. We convert that to an egg. Yes. On this body compiler. And that returns the egg ID of the expression that is returned. So then we have that. Yeah. Maybe we do like this, you know. We define all of the compiler, the body stuff, and then we actually compile the stuff, and then we define an egg. Why is it this weird? Oh, I know, because it was in switch, right? So here we just have function.push an egg fun with a name. Yeah, the name is the, you know, the fun name. What else does it have? It has parameter types. Params or stuff like that. Yeah, params, which is a slice of egg types. Yeah, we kind of need to create that actually. Oh. Yeah, we need to create that, and we need to, you know, resolve those types. Yeah. Yeah, we need to basically compile the signature as well. So we have a list of egg type, and then for each param in fun, the params, you know, basically we want to say convert this type. Maybe even do that. Ooh, yeah, sure. to convert that to an egg using this toast, because in order to do this, it will have to basically go through the definitions and resolve all the type calls that we have. Yeah, and we still need to implement that. But yeah, we can basically then push that like this, and return type is fun.return type to egg using the toast. Then in here we can say we have the params. Oh wait, oh, this would be so nice. And the return type and body. So the impl is an egg fun impl.code with code. You know, egg code containing the body, basically. I think so. Oh. Yes, this is so beautiful. Okay, the fun compiler, we can rename that to code compiler, because it doesn't care about the function parameters or stuff like that. It just cares about creating code, and that's actually like semantically so contained, so nice. Okay, and what's more, I think we can even, like, all of these, like this and this and this, they are independent, so let's maybe inline them here. Yeah, let's remove this. Let's take all of this down here. Kind of, yeah. Yes. Whoa, look at this beauty. So we have functions up here. We push the built-in functions, and then we map the toast functions. So we just create an egg fun with a name, with parameters. Parameters are just, you know, the mapped parameters. We push those, and then we return those. Return type is the return type converted, you know, like structurally resolved, basically. And then the implementation is eggfunimpl.code with some egg code. And egg code has expressions, which is just this, basically. And it has a body, which is the body that is returned. That is beautiful. That is seriously beautiful. Is it like that? Like the egg code? Yeah, expressions and body. Nice. Nice. This needs toast type. No. Egg type doesn't need toast type. That's nonsense. Nonsense. It's an egg type. Yeah. Built in with nothing, but it expects, it needs a built in. Alright. Sure. We can do that. Yeah, eggfun tried to assign list egg type to field params of. Oh yeah, params needs to be converted to slice. Sure, we can do that. Then in here we have the function funs. It's not a field of toast, it contains defs. Oh, right. True, so not each definition is a function. that is true. That is very, very true. So basically, if def is fun, only then we want to do this. Okay, nice. Oh, def is not an enum. It's not. Wait, def. Oh, def has a name and stuff like that, right? Toast. What did you do? Okay, so we have a name and a kind. Okay, I see. Yeah, I guess. I mean, we could just have like if yeah, I think we could just it's more elegant if we put the name inside of the type def and the toast fun. Yeah. Yeah, because then this is just, you know, a def of either a type or a fun. Toast type def, sure. Let's do it like this. And then in here we just say, you know, to toast type def can actually return toast type def, which makes sense. Because now the toast type def, you know, the name, we have a place to put the name because we didn't. Before we couldn't do that. Now we can. And similarly in the, yeah, I know. In here we need to then push type def dot, sorry, toast def dot type with the toast type def or something like that. And this will be the same, toast def dot fun. Yeah, but of course that needs to return exactly a toast fun def. So toast fun def, right? Or toast fun? Just toast fun. Toast fun needs to return toast fun. Sure. Look at how much more elegant the code gets. Okay, def.name. No, that's not how we do this here. We have to do that in the switch, but that's fine. Yeah, just like this. Cool. And then, now in here we can check, you know, if this is a function, then we do stuff like this. This code doesn't work, true. We don't like lower types yet. Yeah, that's actually lowering types. To egg, you know, we have type, which is an sorry, a toast type def. A toast type. Yeah. And we have a toast. And it returns an egg type. Basically, we just switch on the type. You know, if it's a variable, then it stays the same. It's just an egg type. The variable. it's a call, okay, that's like the one complicated case. Yeah, we basically need to go through the toast. If def is type definition of some type, then if the type name equals the call receiver, is a call receiver, maybe. But if it is, then yeah, we basically want to compile that definition with concrete arguments. So I think I'll need to add toast type. Here's the toast, and this is basically the type mapping, which is a map from a variable to a concrete egg type. Yeah. And this entire thing returns an egg type. And this is basically just, it just calls to this other thing. And this then does the actual work. So in this case, if the call is a receiver, we have a call type. Yeah, we basically need to, like if the env, contains the variable, okay. Yeah, sure. If this is some type, then we just evaluate with that, otherwise to the variable. And if this thing is, you know what, let me make this more concise. Okay, either type or the variable. If it's a call, then basically the first thing we do is we compile all of our arguments. Or rather, yeah, we do it like this. Yeah, so we found the matching type. If there is none, referenced type product. Type doesn't exist. Okay. Yeah, and here we basically want to create our own mapping. So basically, we need to make sure that the type definition, so the def params.length, that is the same as the call args. instantiate def.name with 1. Yeah, something like this. Okay, yeah, now we know they have the same length, and you know, to do check that no name exists twice, or rather we should do that like somewhere else. Yeah, let's just ignore this for now, and then we will hopefully probably remember that. Yeah, so for for both in zip of def.params.iter and call.args.iter, basically, you know, we have the parameter name and we have the concrete argument. So we want to first arg is both .b.toEgg type toast end using our current environment, and then we have a concrete type and want to insert that in the mapping. So mapping.put a arg. Yeah, I'll explain in a minute what's happening here. And then we want to basically compile that type. So def.value.type. What's it called? We have this type definition, and it's a type. Yeah, type.toEgg using the toast and the mapping. Yeah. Okay, so what's happening here? Yeah, enums. What's happening here is that, let's say you have a type such as you write int in your code. Here we basically need to check, you know, if called receiver is int, then we need to assert that call.then equals isn't. Oh, name and args. Sure. Yeah. And then this evaluates to, you know, egg type.int. I'll explain this right now. Okay, so well, I'll fix it later on. So the idea is that if you can write something like this in your code, or you can have a definition of like list of t equals buffer t, and I know we don't have structs yet, but you know, buffer t and int, for example. And now the question is, we have some kind of type, no, you have, let's say you have a list of int. This is in the toast. So, you know, in the toast you have several definitions, and some of them are type definitions like these. And the question is, I have this list of int in my code, and now I want to like compile that to a concrete egg type. Or even, you know, if in here I have a function foo that accepts a list of int, and A, which is a list of int, and B, which is a list of t, and then it returns something, I don't know. Then basically, when you look at this, what's the list of int, what's the list of t, we want to convert those types into egg types. So for list of int, what we need to do is we look at this, we see, oh, this is a list. Okay, list, this is a call. It's none of the built-in types. So then we look through all of the toast definitions, look for one with a matching name, which is this one right here. And now we basically want to copy this to where list is. Except that each time in here where t occurs, like right here, we want to replace this with int. And that's what the environment is for. So the environment says, please map this lowercase t to the int type. And yeah, we can basically just create this environment map by checking, okay, the list definition has one parameter, t, and we also pass in one type, you know, int. So that's perfect. And then we zip those, which doesn't work for some reason. Oh, because they don't need to be mutable, I think. Interesting. To egg. Oh yeah, don't need this. Yeah, okay. Okay, so yeah, basically then we say, okay, let's map this t to the int type. So in this environment, we map t, which is the parameter name. We map that to the type, and the type int. Before we like put that into this right here, we convert this into an egg type. So for example, let's say you have another definition, like map key value is, like this doesn't make any sense, sure, but let's say we do something like this. We don't, you know, if we then see I have a map of int string, we see, okay, what is map? And then we don't just want to like copy the definition of this to here, you know, like a list of kv, and then we have a list of int and string, and then we need to look up what is list again, and then we can map those. But instead what we do is we first convert these to egg types and say map, and then say, well, okay, now that we have egg types, just basically resolve, now that we have the egg types, key is int, v is string, now please compile this right here. You know, compile this with this type environment. And then again, this will first, before even resolving the list thing, it will replace all of these right here. So it will first convert the arguments two egg types. So it will convert this k to int, and then it will resolve list int with other things, like with, for example, in list int we have a t, so it will then be like, okay, I want to resolve this with t is int. If we wouldn't do this first, you know, convert types to egg types and basically try to resolve list of k with, you know, t is a k, then we could have some sort of like collision where like multiple types define the same type variable, like with the same name basically, and they would collide, and we don't want that. So yeah, we first resolve those, and then we compile them further. Yeah, I should like have some comment for that, I think, but yeah, for now it's fine. Yeah, all of the built-in types are special cased. We need to make sure that we don't pass any arguments to them. Yeah, and for enums, we basically need to just lower all of the variants, you know. The variance is mapped from string to slice of egg type, and then, you know, for all of the for each variant in enum, we basically want to put that into the variance map with its name and its value, but the value mapped, of course. So the the value right now, this is just a slice of some stuff. So we need to map all of the arguments to tag types. So for each arg in variant.value, which is the list of arguments, we say we push arg to egg toast and type environment. And then here we can say arguments to slice. So that down here we can then say we want an egg type enum using these variants. Okay. So this call doesn't work because why doesn't it work? I mean, it's nice that these work, you know. Lowering the body doesn't work. We have a to egg with toast. No, it should be toast expression. Yeah. Let's see, we have the egg fun compiler, which by the way I want to rename to egg code compiler, because it's like only the implementation of the function. And we have an egg code compiler, sure. Yeah, and we can convert a toast expression using a body compiler to an egg ID. Creating egg expressions, nice. And instead of definitions, we have variable definitions, which, you know, they also have a name and a value, just a different name. And this doesn't exist, and this, it all makes sense. Okay, for the visible things, here we say lookup, or we say unknown reference name, sure, and that is just a local egg ID. Sure, you can't reference globals for now, and I think that's fine. Yeah, we do need to handle calls differently, I think. Yeah, because now the receiver is not just wait. Oh yeah, we need to basically we need to make sure that the receiver is a name and nothing else. yeah, call receiver, just switch on that, I guess. Switch on the receiver. Or if it's name, then everything is fine. Otherwise, it's not fine. Yeah, so basically we could also just say that name or panic called non-name. No, if this works, but oh, yeah, sure. Let's do it like this. Okay, so receiver is just a string. Yeah, this has a local value. Sure. What's up here? Try to assign a list of egg type. Oh no, we want to take the slice, of course. And then even further. We're printing. That's super cool. Yeah, printing an egg type doesn't work. True. We don't do that yet. So we need to add that. We want to print a type, which is an egg type, which means we switch over that type, and if it's, you know, we print all of those differently. Of course we do. Yeah, so I don't know if it's, I guess something like this. I mean, not for variable. This is just like this, never enum. Okay, yeah, for the enum, we basically do something quite similar to how we do it for the toast, which means that we go over all of the variants. So, and we print all of them using like a space and then the variant key in parentheses. Oh, right, they can be multiple arguments. So then for each arg invariant value, we print that, and then we are done. Okay, cool. And there is another error down here, code.get. This call doesn't work. Okay. Oh, only works on egg fun. Yeah, this should be egg code, actually. Sure, like this. Nice. What's here? Global is not. Oh, sure. Okay, no error anymore. Whoa. Crazy. Yeah, true. This is not a valid function body. That's very, very true. Yeah, that's, I don't know. Okay, buffer doesn't exist. That's, yes. Yeah, I mean, we don't use lists yet. Oh. Let's say, I mean, this is like a nonsense definition of lists, but I still. What? I mean, that's nice. Nice. We have this toast with type definitions and function definitions and so on. And that gets converted into this, and you can see that the a list of t is defined as an enum containing one variant called list with a t and an int. And here we have main, which accepts a list of int. So this gets converted into an, it accepts an enum with one variant called list with int and int, and it returns an enum with true and false. So out of the types, they get resolved. What? That is sick. That is super cool. What? Okay, okay, I like this. I like this. Let's add some more parentheses, because why not? Yeah. Main returns a bool. You see? Returns an enum of true or false. Whoa. Whoa. Crazy. Okay, how about, what if we have a generic function? Let's say I write get takes a list, which is a list of t, and it takes an index, which is an int, and it returns a t. And let's say it just returns 5, because I mean we don't type check anything yet. Okay, okay. Whoa, this is still generic. Okay, so yeah, here we have a list of int, so this gets like propagated and like structurally typed into this type, and this accepts a list of t, so there is still a type variable in here. List of t and int returns a t. Wow. Wow. Wow, that's nice. That's super nice. Yeah, I think I'm going to eat lunch, and then yeah, we'll continue with the next compiler stage and actually like implement function overloading and type joining, and okay, like we have joining of types, like but like checking if two types match and stuff like that. Ooh, this will be fun. Okay, yeah, see you then after the break. Okay, well, yeah, let's implement the next stage, yogurt. Right, but before we do that, I want to basically draw something, because this will work differently than it did until now. Until now, we just, let's check the yogurt. We had these yogurt expressions and values and types. And basically, the distinction between values and types wasn't quite like there was no hard border between those. For example, if you have a number 3, then the value of that is actually just comptime, because it's comptime known, and the type is comptime int 3. So yeah, the type of that was basically like a comptime int 3, and the value didn't really exist. And that was kind of fine, I think, but yeah, it turns out it makes some things more difficult, and I think we need to change that in the new version of the type system. So let me switch to my iPad and draw stuff. Right. So the problem is, like, the reason why we redesigned the type system in the first in the first point was that we wanted to support recursive functions and recursive types, because that's like you need that. You need types that can, you know, be like dynamically sized. You don't just want a struct with a fixed layout and then, you know, you only have this we need data structures that can scale with the amount of data, and that's not possible otherwise. So yeah, what we did until now was that we analyzed we tried to figure out the return type of a function by just looking at the body. So for example, if you have a function called, let me pick a better pen, a function called foo with an a and a b, you know, and we were like, okay, let's figure out what the return value of this function is. So we would then actually look at the body of that function, and we're like, okay, this function is called with you know, with an int and another int, and we look at the body and see what other functions are called. Like maybe this calls I don't know, the plus function with a and b. So then we would compile the plus function for int and int, and then figure out, okay, so this returns an int, nice. And then we would know that this right here is an int, and basically we work our way through the body of the function and figure out the type of everything, basically infer everything. And that doesn't work if the function calls itself. So if this is a recursive function, because if this function like calls, you know, foo ab again, then in order to figure out the type of that, well, we basically need to analyze the function, but that's what we are doing right now. So the type of the function would depend on the type of the function, which makes no sense. And that's like even worse, because you can even analyze the type of that. There's the type of built-in and the type info built-in, and they basically allow you to inspect the type of that, and then depending on that do different things. So we could have a function that looks at its own return type, and then based on that it returns something different, which is bad. Yeah, this is kind of fixed, or at least I hope it's kind of fixed, because now we require type annotations. So we know that a is an int and b is an int, and this function returns an int. So now when we analyze the body of that function, you know, then if there is another call to like foo with a and b, well, first of all, we can check that a and b are ints, because otherwise this is an invalid function call. But then we also know that the type of that is int. So if you then inspect the type and do stuff like that, that's totally fine, because we can rely on those type annotations. And a problem only occurs if we want to specialize functions with like what I just showed you, the values. Because now let's assume that 5 is also a type, you know, and we want to specialize this function for the type 5 and an int. like basically anything that is more specific than the arguments here, then we don't really want the return value of the function to be more precise. And maybe let me give you an intuitive example. We may have I don't know, implies function that takes an A, which is a bool, and it takes a B, which is a bool, and it returns true. But now let's assume that we know this function is called with a false and some runtime known bool. You know, we know that the actual types are the actual types, they are true and bool. What's the return type now? And I think the only consistent way to answer that is to basically acknowledge that the return type still has to be bool. So this should be bool. Yeah, and for this it also has to be bool, even though, you know, if you don't know, implies is like the mathematical implies looks like this. You know, you have this implies function, and you have an A and a B, and yeah, let's do it like this. If A is false, A can be false or true, and B can also be false or true. And if A is false, then this results in true. Like, you know, from something false, you can always imply something true. But if, you know what, let me actually choose some more. I can't just say, let's look at the OR function. Yeah. If we call OR with true and bool, then we know that the result will be true. And the question is, you know, if you have something in your code that basically says this, foo is OR with true and, I don't know, some bar. And we know that the type of true is true, and the type of bar is only runtime known, it's a bool. Then what do we want the type of foo to be? Do we want this to be true? Because we know that this function will return true, you know? If OR returns true if any of the arguments are true, and we know that the first one is true, so this will definitely result in true. But I'd argue that we don't want the return type to be this. So basically, if we then inspect the type of foo, then we will instead receive bool, even though it's less precise. So basically, I'd argue that we don't specialize functions based on the body. Well, we kind of do specialize them based on the body, but for the, looking from the outside, you know, as someone who calls this function, if one of the arguments is not comptime known, like this bool, for example, then we will not use the more precise type that this results in, but instead we'll use the general type that the function signature implies. Because otherwise, what if we have, I don't know, what if the OR function calls itself with A and B? Then we basically have the same problem. In order to figure out the type of OR for true and bool, we need to figure out the type of OR for true and bool. So we have the same, exactly the same problem, just that we have a rough idea that it returns a bool, but we don't know like which specialized version of the bool, or if it's specialized. Yeah, so the basically the rule that I want to implement now is, you know, if all of the arguments are comptime known, then, you know, just this results in a comptime known result. Just run the function, calculate it. And if any, like on the flip side, if any arg is runtime known, then the function should only result in a runtime result. Yeah, and that's basically similar to how Zig does it. And it's a lot more intuitive, I think. So right now we have basically like values. So for example, right now we have our value 5, which is compile time known. But we can also have, I don't know, an enum with where we basically know the variant. We know we have, I don't know, sum, you know, we have some function that returns a maybe int, basically, but we know that it's the sum variant, but we don't know what's inside. So we could have this. And this is not good. Basically, we don't want these like partially comptime known values. I think at a later compiler stage, when we do optimizing and stuff, maybe we want those, but right now we don't want them to be observable from user code using like type of build-ins and stuff like that. So either have everything comptime known, or just have everything be runtime known, like only operate on the type level, but never have something where only part of the value is comptime known, you know, where we basically know, well, the surrounding thing, it's a sum, but some part of it, we don't know that at comptime yet. And also I'd argue that even for something like, you know, sum 5, even if this is like completely comptime known, oh, well, if you call type off on that, it should still return this. So it should still return maybe int. So basically types don't get more precise automatically. You can do like switching on types and like calling type info, and then, you know, you have a big switch. If it's an int, I want to do this. If it's something else, I want to do this. But you can't you don't get these concrete things. Like the entire type solving, the entire overloading, the entire function resolution and all that always just works on the type level. Yeah, that's basically the plan. Like disallow this and instead only have values which are comptime known and which contain type. You know, they know their type. Or just have runtime values which only have a type. Right. Okay, so we want our yogurt expressions to be either of those two. And yeah, right, that's actually like important for functions like you know, a parse function which takes a JSON and a target type, and it returns that target type. We want to allow something like this. But basically, whenever you call this function, that's the point when you realize, hey, this function returns this parameter. So this has to be compile time known, because we need to know the type, like the result type of this. Yeah. Okay. So let's do that. Let's implement that. Right, here we have the yogurt. And I mean, this basically stays the same. We have some functions with signatures. And yeah, I mean, this is kind of weird. We may change that to like actually containing the, you know, the types and comptime values and stuff like that. But okay, a function has expressions. Seems fine, I think. Yeah. Here we don't need that separate body like we did in the egg, because there are no built-in functions anymore. Sure, there are like instructions inside of functions, but functions themselves, they are all uniform. They all just have expressions and a body. Yeah, the signature, functions don't need to contain the name or names of parameters or something, because, you know, like they are completely known at compile time. Like they are completely resolved. Right, so let's look at the signature. The signature, I want to change this, but I'm not sure if I should change it now or if I'll rather like look at this first. Yeah, I think let's look at the function body first. So body has some parameters. It has expressions and it has a return value. Sure. And expressions, this is the interesting part. They have a value. They have a value and a type. Ooh. I'm not sure I like this, to be honest. I'm not sure I like this. Because in this case, values are not really what I would call values. I mean, switch is not a value, right? This is more like an expression. But then expression is already used for this. So, yeah. What do we call this? But I can like define a yogurt value for now. No, a value should either be like an int with like a known int. It could be a string. It could be a concrete enum tag, perhaps. Yeah. Which basically means, you know, this a string and a slice of other yogurt values that are associated. Yeah, we don't do that now because we basically resolve all function calls directly. You can't like create function tear-offs and store functions and stuff like that. So we will remove that. We'll also no longer have these, but instead the type will basically be similar to this right here. Like we don't have type variables anymore because all types are concrete, but with int, string, type, never, yeah, and enum. Cool. something else? I'm not sure. Yeah, okay. So this yeah, I think a value must have a type and like a kind, yogurt value kind, and then there's a yogurt value kind containing the actual data. And this is not really a value, but more like an operation or expression or something like that. Okay, so yeah, this is good. We have yogurt types. This is fine. We have values with a type and a kind. The type is defined above. The type is this right here. It's either an int or a string or a type. And then we look at type, yeah, or a tag. Yeah, never is like a never yogurt value never exists. Not at runtime and not at compile time. Yeah, tag is basically, you know, this right here. But only one variant from that. Okay, cool. So we have this. Then the next step would be to have a yogurt, and I don't know how to call it, like yogurt operation, expression. I want to call it expression, but that's already used here. Maybe operation, yeah. I don't quite like it, but okay. Yeah, and this comptime actually means, hey, this definitely needs to have a value. Oh, yeah, and these expressions that just have an operation. Yeah, they have an operation that results in a specific type, and maybe they also have a value. But not all, like not all values are comptime known. So this is a maybe. Okay, yeah, then we have the type. We have yogurt values, which have like an associated type. We have yogurt operations. Okay, which can either be referred to a parameter, just, you know, create this comptime value, switch on something, create a tag, call something, and so on. Okay, okay. So next, comparing stuff. How do I want to do this? Yeah, I mean, types, they're just int, string, type, and never. You know, okay. We can condense this a bit. Nice. So this int, string, type. Yeah, this is like an imperfect hash, definitely, but I'm fine with that. Okay, so we can compare types. Let's compare, I don't even know, values, perhaps. But not really, like, we don't need that. Let's just stick with this and then we'll see what happens. Right. So you can get a yogurt signature. And yeah, this is, so basically for each function, we want to compile a separate version where the arguments are either comptime known values or runtime known types. So I think the way to do that would be to have something like args. I want to say args. Yeah, that's doesn't make sense to have like a yogurt info. Oh, that's such a, like, I hate that it's such a generic word. But basically I want to check, is this a runtime thing or is it a comptime thing? You know, it can be either one of these. And then we just have this. Yogurt expression has yogurt info. Oh. Maybe. Okay. Yeah. And this would basically take info. We have a string builder, and for each info in the args, we say, hey, we add that. Okay, sure. Then yogurt signature. Wait, do we have? We don't have. Oh, here's the writing. Sure. Yeah, you can create a signature, you can equate to signatures, and you can hash one. Okay. So writing a yogurt basically tells us we write the signature and then the body. Sure. And the signature, the signature, we can also provide that directly. So let's do that. Yeah, IDs are just the end. Writing a body of a function means, you know, doing stuff. Sure. Writing a yogurt. Ooh. Operation, I think it was. Still feels wrong, but okay. I hate this. Yeah, maybe just switch on the expression info. To be honest, I hate this. I hate the name info. I hate. This is basically what we want, but the names. There are no good names for this. Yeah, let's revert this to the type and value, which is a maybe value. Okay. And this, I mean, we still want this basically. Could say this is a little bit arg maybe. You know, when a signature has, it needs args, something like that. Okay, yeah. Anyways, here we have that takes args. That's at least consistent, you know. Although really, these are more like params, come to think of it. Because these are basically, you know, from the point of view of a function. You either get a runtime known thing or a comptime known thing. Okay. You know, at some point we will. I think it just takes a lot of time to find clean abstractions, and we're not. I don't think we're quite there yet, but at least it kind of works, you know. Okay, so writing an operation, if it's like comptime thing, we don't need to do anything. It's a param, it's a switch, it's a tag, call, cast, instruction. Okay, fine. Yeah, up here. Yeah, this is where I struggled. This should work. We have the type. And then, you know, if exploitable value is some value, basically if the value is comptime known, then we also want to print an equal sign and then the value. Okay. Sure, we can write types, but not these at all. And we can have a type, which is a type. Oh, wait. Type of this is string. The type of this is string. The type of type is type. Yeah, true. Type doesn't have anything associated with it, right? Nope. Okay. So we have type, we have never, we have enum. Okay. Yeah, we should do the same for values actually. So, you know, just the values. Once we switch over the value, if it's an int, we just print the int. If it's a string, we just print the string. If it's a type, we just print the type. Yeah, this doesn't exist. Tag exists with some data, and it just prints the data.tag, and then for arg in data.args, it also prints the argument like this. Oh, here let's do string.debug so that we have quotes around it and use backslash n and stuff like that. Okay, so this this doesn't really work, I'm afraid. Nope. Which is sad, you know, but maybe let's add 2 of these. Let's have these like yogurt value. Does this make sense? Oh, right. There should be operation, yogurt operation yielding type and a value. And here we use the operation, and the value is some value. Whereas down up here we have the operation, and value is none. Okay, cool. I'm not sure if like that's exactly how we want things to be, but okay, we have a fun compiler. We can add a mapping, sure. We can look up a thing, I guess. We can convert egg to yogurt, yeah. We just go over the funds, we get maybe. Oh, no. Funds is a list. So we need to find main. Basically for fun in the mains, maybe. Because it's also an error if there are multiple ones. So for each fun in egg.funds, we basically check if fun.name. Oh, no, if fun is fun. No, if fun.name equals main, then mains dot push fun. If mains dot len is not 1, then we just panic. Otherwise we evaluate to the only item. Yeah, so this is an egg fun. Yeah, it only takes 1 parameter. Nice. But not the body parameter. We'll just check the parameter directly. Main.params.get0 equals yogurt type.int. Let's say, yeah. Or we panic in any case. Okay, then with this yogurt, we say main, convert yourself to the yogurt. Main to yogurt, yeah, params. But these won't be the types, but this will be yogurt params. And this will be yogurt param runtime and yogurt type int. Yeah. Right, so we have an int that is only runtime known. Cool. So then in here we say, please convert this body to yogurt. These are the params. Yeah, and I know there is like, oh, I hate this. Param IDs, why not? Yeah. And then, you know, for the params, we basically push a new thingy, an operation in this case. yeah. Like this, I believe. Yeah, an operation and oh, I see. Okay, you know what? I think having a dollar is still fine, because in this case, the value still has a type, right? Like this. Yeah, that's cool. So we can just say yeah, this should still work. Well, okay, it doesn't work, but we can make it work. We basically only need to switch on the param, as it's a comptime param. Then it's a value basically, and we say operation $value. If it's a runtime thing where we only know the type, then we say it's an operation with this type. So we call either one of these. Okay. Yeah. So this will just work. We push the params, we have expressions, we say, hey, please convert those expressions to yogurt. And then we create the yogurt body. Nice. Then we have mappings and so on. Okay, so converting an egg expression to a yogurt expression. That's basically where the magic happens. Basically all of the yogurt value stuff in here. Is instead yogurt operation. Oh, you know what, let's call it yogurt op, just because that is so much shorter. Okay, does it? Yeah. You know, like concise code. Okay. Yeah, so we have yogurt op comptime. Yeah, we don't need to do anything. Yogurt type. Oh, sorry, yogurt value. Dot int and dot string. We know the value at compile time. Then for a symbol, actually yogurt value tag, sure. And this is a tuple of the symbol and an empty slice. Yeah, this should be unreachable because the only parameter things they get compiled outside of the function body, I think. Yeah, global doesn't even exist. Yeah, a switch is just param. Does param exist? Egg expression. What is param? When is that created? I mean, yeah, okay. Oh, push param. Oh right, yeah. It's in the egg code, but it will never occur inside of a yogurt body. So we know this is unreachable. Okay, that makes sense. Okay, so then there's a switch, which means we look up the switch condition. We check the type, correct. Oh, yes. Yeah, okay. And basically here we can check check that there are no other variants handled. And to do, if the condition is comptime, only compile the corresponding branch. Okay. So condition is this. Yeah, basically I want to do, you know, if the condition is comptime, do something else. I'm going to do that later, I think. Right now, I'm gonna make sure this is handled. Yeah, so we have the type of the condition, and we have the variance, because we know that it is an enum. If it's not, then that's an error, sure. Then we have the cases, and we basically check that the case is handled. Yeah. Now we also want to check for, you know, case in switch. Dot cases do condition variance dot contains case dot key, or panic handling, you know, but that variant doesn't exist. Beautiful. So check it in both ways. Like exactly for each variant of the enum, we need to handle that specific case. We can't have too many cases, we can't have too few. Okay, yeah, maybe let's do that first. So for each case and switch cases, we ensure, yeah, we do this. And then we do that. And yeah, okay, that's cool. Find the common type of all branches. Sure, we do that. We add cast expressions where necessary. Sure. And these are like runtime casts, which I think for now is fine. But we may look into those. Okay, then we have this switch with a common type. Nice. So then there is the call. Oh, and this is interesting. Oh, this is cool. So compiler.lookup. Problem is the receiver is a string. Yeah, basically this is handle overloading, or like find function. Yeah, right now I'm just going to comment that out. Sure, then we have a bodybuilder, and what's this? Like, yeah, for built-in functions, we do some stuff. You know, let's just compile this and we'll see where this goes wrong. It doesn't, oh, is that it's not used, right? Ah, yeah. Now it won't compile. Yeah, that's what I thought. Okay, so, oh, comparing an egg type with a yogurt type, that seems wrong. Yeah, 209 yogurt. Yeah, right. Yeah, basically we need to look for a function, but in order to do that, we yeah, we may have to, like, I think it's fine if you know, define a function like this, main stuff t. You know, if main is generic over this, that's also fine. You know, this will be compiled for t equals int. So we need to think about how do we look up functions in the yeah, how do we look up functions? Yeah, there was so much weird code in here, I think. Like, this is quite a long file, and you know, maybe we'll refactor that at some point. Yeah, we have like writing of all those different things, and then, you know, we go on with looking up functions in the egg. That's what we want to do. Whenever a function is called, we need to choose the correct function based on the name and argument types. Yeah. So basically, get. I want some lookup, you know, that you call an egg, and it returns you an egg fun. Yeah. And you give it like a name and the types, which is a slice of yogurt type. Probably. Yeah, those types, you know, they should not contain variables, like for example egg types do. Those should be very concrete types. Oh yeah, it doesn't just return you an egg fun, but also like the substitution map for that function. Wait. Yeah, okay. it's fine like this. Let's just think about how we would do this. We go over the egg funs, and basically we check is the fun name, is it the same? And then we have this thing of this list of functions with matching names. And basically we say name matches, but push the fun. And then we check if name matches is empty, then yeah, this should probably panic, I think. I know later on we will use results for everything, but right now there is no function named name. Okay, then we have the name matches. And then for each of those we need to check if the arguments match. So full matches, there's another list of egg funs. And basically for each fun in the name matches, we just check if the, well, now it gets kind of complicated. We want to see, we want to basically unify an egg type and a yogurt type, right? Yeah. All of this we want to check is this assignable to. We want to see is this yogurt type assignable to this egg type. And then this returns a map from the egg type may have like type variables. We may have this. So basically when we say, we can ask something like is assignable int to int, can we assign this? And it just says yes. Here's an empty like replacement set. When we ask is int assignable to string, it says nope, no can do. If we say is int assignable to t, it says sure, and t has to be int. If we ask is list of int assignable, something like that, assignable to list of t, it also says sure, int has to be t. And we ask is map of int and string assignable to map of t and t, it should say no, that doesn't work, because then t would have to be int and string at the same time. So yeah, we want to have this matching of types. We have a concrete yogurt type, and we want to see is this assignable to this egg type, which may contain type variables. And either it doesn't work or it does work, and then we get a map from what the type variables, like the types of those type variables, need to be for this to match. Oh, we also probably want, like, if we have a never type, is never assignable to int? Probably. Yes. Yeah. Okay. Okay, we can do this. Yeah, it's assignable to. Is this yogurt type assignable to this egg type? I mean, we basically need to switch over the yogurt type. If it's an int, I can like paste that. here is a documentation comment. Checks if yogurt type is assignable to the egg type, possibly containing type variables. Of what values the type variable for the mapping to succeed. Yeah. Yeah, let's just leave it like this. Yeah, is it assignable to this? And then the answer is nope or yes. Never to int. Yeah, and oh, what if we have is never assignable to list of t? Then we also say yes, this works, but we don't even specify the t's. This is kind of cursed, to be honest. Maybe let's not do this. Yeah, let's say that never is only okay. Yeah, for now let's not do that. Okay, so we switch on the yogurt type if it's an int. Oh, I think it's actually easier if we switch on the egg type. Yeah. Yeah, that makes sense. So we want to see, hey, we have this egg type. Which one is it? If it's a variable, then actually this works, you know? Then we just return some map that maps that variable to the yogurt type. If the egg type is int, it expects an int, then the yogurt type has to be yogurt type.int. So yeah, if yogurt is int, then it works with an empty map. Else it doesn't work. Okay, similarly for strings, you know, if it's a string, it does work. Similarly for types, and now, yeah, oh yeah, actually similarly for never, you know, if the only thing we can assign to never is never, can't assign an int to something that expects a mapping. Yeah. And an enum. Ooh. We basically want to check all the enum variants. Just something like, you know, true or false. Is that assignable to true or false? Like, okay, maybe true or bar. Is that assignable to true or bar or bus? I think so. Yeah. I think that works. Ooh, okay, so it's only that each variant needs to map to a variant. So each variant in the in yogurt.enum, and yes, this has to be an enum. So if it's not, then we just return none. And for each of those, maybe factor this out. Yeah. For each variant, we basically check if the enum maybe of that type, of that key, you know. If that works, if that exists, well, okay, if that doesn't exist, then we just immediately want to return, you know. And yogurt args is just variant.value. Get the egg args, then we assert that they have the same number of arguments. Or it doesn't work. Yep. And then well, then we want to check if the individual arguments are assignable. So basically we want to check if I don't know, like for both in zip yogurt args.iter and egg args.iter. For each pair of arguments, we want to check that both.a is assignable to both.b. Right. That seems reasonable, I think. Okay, so this then returns a mapping. And we need for all of them to be consistent. You know, if we have, I don't know, foo int and bar string here, and then in here it says, well, we have a type foo t and bar t, that doesn't work because t would have to be int and string. So those mappings that we get from this, they also need to line up. Yeah, so let's do this.
and then arg mapping. Yeah, and then we have like one total mapping, which is map from string to yogurt type. And then for entry in arg mapping, we basically want to check, does this entry already exist in our global mapping? So if mapping.get the entry key, you know, if that is some value, some concrete value, yeah, some concrete yogurt type, then we just want to make sure that they are the same type. So then we want to make sure that type is entry.value, or we return that's not possible. Otherwise, we, you know, if it doesn't exist in that global mapping yet, then we just add it. So mapping.put stuff. Okay, yeah, we do that for all payloads, for all variants, for all everything. Cool. That's actually, the enum case was more complicated than I thought it would be. But sure, and if like there were lots of possibilities where we just return none, where it doesn't work. I don't know how to format this nicely. Yeah, if that, so there are lots of these return thingies, and if none of them are taken, then this worked, and we have this global mapping that unifies all mappings of the variants and their payloads. Okay, right, so let's maybe check where that fails. Oh yeah, same thing. Right, we just wrote the isAssignable2 function, and now we want to use that. So here we're looking for a function with that name, and that takes those types. And we basically want to, yeah, we want to check yeah, we want to check are the arguments assignable to something. So basically, you know, we have the types up here. Are those assignable to the function arguments? Which will actually be pretty similar to this, I think. Let me just copy this. Like yes, it will be different. Like we don't have variants or something, but we do have a mapping. And then for each argument and the types, which is a concrete type. Oh right, we should check that they have the same length. Arglen matches. I will just do that right here, because why not? We have fun.args dot sorry, fun.params dot length equals types.len, or we just continue to the next function. And then we create a mapping. And then for each, oh yeah, we basically want to do this in a more limited form. So we go over the types, and we could just call them args, right? Yeah, we go over the args and the fun params, and we check that they are assignable. Yeah. Or if that doesn't work, then we just, yeah, we basically want to continue in the outer loop. So yeah, that's bad, but okay. Yeah, we have this arg mapping, and we have these entries in there. Yeah, and we basically unify them in this big mapping. And then, well, if it doesn't work, then we continue. But if it works, oh, we shouldn't refactor that, I know. But we just push the function to the full matches. We could also use the like the mapping. I'm not sure if we need that actually, because I think we don't need that anywhere, because then we compile that function for like concrete types and values and everything, and that's totally fine. Yeah, and inside of the function we never have any yeah, no, I think we can't even like reference the type parameters right now. Like we may change that, sure, but until then, I don't know. Okay, so yeah, what we really want is, instead of all this, we just want to say egg.lookup with a name, main, and with a yogurt type, and that should give us a function. Or we panic, no matching main found. Oh, sorry, this doesn't even return a maybe. It just works automatically, I think. This call doesn't work. Lookup. X string, oh, and a single yogurt type. No, this should be like a slice. Okay. Yeah, so we'll probably have, yeah, other errors here. Nothing. Previous case is the pool mapping the put. For entry is 237. 237. Oh, I see. This evaluates to bool because, yeah, you know, sometimes it's kind of weird to use OR as control, so I may have to change that. Inconsistent return types. Expected egg fun, found stuff. 178. Oh, that seems like something I copied from down below. Yeah. I if that doesn't work, if the types can't be joined, then we just break. And yes, also here, this is just nothing. All right, it returns nothing. So basically we need to check that there is no matching named flip for types args. Okay. Yeah, if name matches is larger than 1, multiple function match name args. Oh, true. And then we just return the single match. So here we create a builder and we can't write a yogurt param. Yeah. So basically we want to switch on that. And if it's a comptime value, we want to stringify that value. If it's a runtime type, we don't know the type, then we want to show the type. Yeah. Is this better? Nope. Because here, yogurt value is not an enum. Oh right, because it has a type and a kind. Yeah. Oh yeah, there's tuple stuff, so this will be like this. Right, here we have the body, which is not a field on the egg fun. True. So we have an egg fun and params string egg yogurt. Yeah, basically we want to check if that's like a built-in function, and if so, then we want to compile that differently. Yeah. Yeah, we want to switch on what kind of function it is. If it is a code function, we want to convert that code body, I think, to yogurt. If it's a built-in function, then we want the built-in to be converted to yogurt. Where did that happen until now? Like built-in to yogurt up here. Yeah, okay, in yogurt to built-in, and here, sure, what we just wrote. And somewhere in, like, what? Oh, in the find call. Oh. So when calling a function, we actually like handle those differently. That's okay. Yeah, no, I like it more that we do that up here. Yeah, that seems like the better place to do that. So yeah, of course, wait, this actually works. That's kind of crazy. Okay, so we converted body to yogurt. Basically, we want to get things from the code. And the compiler is a yogurt fun compiler. Do like access the params or something? Nope, we don't. We totally don't. Down here, and like compiling switch param. Okay, never mind. Yeah, you know what? Let's just say the yogurt fun compiler. Let's maybe call it yogurt code compiler. You know, because it's compiles the code thingy. And it just has the code, the egg code. So yeah, of course, when you create that, you need to have the code, which is the fun code or something. Oh right, yeah, this actually depends on the variant. So in here, yeah, that makes sense. We just take the code and compile stuff. For the built-in, we actually, you know, we use the same built-in not to yogurt. Where's that? Is that down here? Yeah, built-in not to yogurt with the archetypes. Crazy. Crazy. The archetypes. No, those should be the parameters. Yeah. Yeah, okay, but this doesn't even need the builder. So let's just omit that as well. Mm-hmm. Nice. Compiler.egg fun .code.get. I like that. I really like that. Yogurt value is not an enum type. Ooh, yes, that is true. Yeah, that's kind of painful. Okay, so yogurt value has a type, which is yogurt type.int, and it has a kind. And the kind is yogurt value kind.int containing the int. And it will be very, very similar for the string. You know, there's just yogurt comptime, yogurt value of the string. Sure. Yeah, similarly for the tag, again, this is something like this, you know, something where the kind is this, and the type is actually an enum with a map from that symbol to the empty stars. Yes, yogurt value. Okay, yeah. Sure. Case.to yogurt. this is the signature to yogurt. And we're basically compiling the body, yeah, the case, and the case is an egg body, and then we have a slice of yogurt types. And they are only runtime known. Yeah. So let's actually like create, params is a list of yogurt param, and then for arg and variant value, we say, hey, we push a new yogurt param with a type, which is the arg type. Oh, I see, yogurt param dot runtime, because this is only known at runtime. Yeah, that seems correct, I think. Okay, so then we have this case to yogurt, and we can just pass in the params. Sure. So params to slice. Okay, so then down here. Oh man. Yeah, when we join types, oh, this gets so much simpler. Yeah, if it's an int, we basically check is b an int. If so, it's an int. I mean, it doesn't get simpler than that. Oh yeah, comptime string doesn't even exist in that case, and strings just checking that the other thing is also a string. Enum, sure, just like we did before, doesn't exist. Never. Actually, let's put that up here. What else is that? There's type. So yeah, we basically need to make sure that both are types. They are the same thing. Simple. Really simple. I mean, we can simplify those further, right? We can just say if b is stuff, then some thingy else, and then we can like join those like this. Yes. Okay, I like that. I really like that. Okay. Yeah. This is the signature. Oh yes, this doesn't work because tyogurt accepts yogurt types. So let's look at the toYogurt for built-ins, which is this right here. Yeah, the params should actually be yogurt params. And yeah, they are kind of, with A and B, if we actually know that they have the correct type, that they are both ints, because, well, we have function overloading and so on, and otherwise this function couldn't be called. And then we basically only need to check is if A is comptime A, then if B is comptime B, well, if both are comptime known, then we basically want to return this, a yogurt op comptime with a yogurt value where the, oh, this is like horrible to write. I hate every piece of this. Okay, so the yogurt value, sure, with a type and a kind. And the kind is the yogurt value kind.int with a plus b. Oh, and we need to fix that as well. And the type is yogurt type.int. Okay, yeah, kind is a plus b, but of course this is not just a and b, because a is a comptime value thing, so we know this is an kind int unwrap, and similarly for b. Yeah, I guess. A dot cast to int. Sure. Yeah, okay. Okay. So cast to int called with a non-int. Yeah. This is built in yogurt type still. Okay. Wait, no. Wait, what? To yogurt. But there is. Oh, wait. This takes yogurt params. It takes a builder first. Why are there. This does not seem right. To yogurt, there are two built in. There's this. Oh, indeed. How do I want to do this? Oh. I hate that it's becoming so complicated. Like, you know, on a conceptual level, that we now have all these different things. We have the operation, we have the type, we have a value. And they may not even like all align. You may call something with a comptime known 5 and the type is int. Or you call something and it always returns true or something, but the type is bool. Yeah. Ooh. Yeah, okay. does it make sense to have, you know, like comptime like I'm thinking, could we just say we have a comptime thing, and then, you know, we basically know the value like this. I'm sure it's not as like elegant maybe, because but we don't need to call something if the value of that is compile time known. We don't need to switch if the value of that is. But then again, there may be like a panic or a debug thing in there. So yeah. Still, it's kind of feels kind of dirty. Kind of meh. Okay. So yeah, this last one apparently should take IDs, I guess. Should take IDs after all. This right here. Then, like, how do we check whether the values are comptime known? I mean, yeah, we can just say we get the ID and then we check if that's okay. Yeah, I guess that makes sense. Yeah. So if builder.get a.value is some a, and builder.get b value is some b, then we have this. And so, oh yeah, and this down here, we basically have an ID and a builder, and we say, well, please get the value if that is some no, this is like totally unnecessary, I think. Yeah, I think we don't need this. No, because we know that those are strings or ints, and the type of those is actually int. Like, whether we like constant fold something later on, that's more of an implementation detail, I think. So with those optimizations, we need to do them later. This right now is only the user observable behavior. So yogurt value is not an enum type. Yes, yogurt value is. Oh yeah, we want to push instruction, and the type is int. Yes. Yeah, this is not like this. But then you know that both of those are ints. So you can do this beautiful thing. And this beautiful thing. And then push a yogurt up comptime with a yogurt value with this type and this kind. Yeah. that doesn't work, then we push a yogurt compare instruction with these arguments, and the return value is just a type. Yeah. Similarly for concat, we just check is the value there, then we concatenate these. Ooh. Now comes an interesting bit. Well, no. So the type info thing, we basically get this right here. We get the type of that. Oh, no. Oh, this type info changed, I think. Type info, yeah, needs to accept a type. Yeah, it accepts a type, and the value of that has to be known at compile time. Nice. Type info, that's not comptime. On type, that's not comptime. Nice. Yeah, so we would basically say this is the type. And then we choose a symbol and then push a comptime thing. Oh god, okay, I can do this. Nope. It's just something like this. Yeah, okay. Yeah, this is already a string, so nothing to do there. This also always works, and we have a yogurt pop instruction which crashes, and the type is never. Ooh, okay, where does this fail? There is no type named yogurt kind. Well, that's true. This is yogurt value kind. Unknown variant yogurt type.comptime string. Yes, 560 is here. The type is basically this should be a yogurt value with some type, yogurt type.string, and the kind is yogurt value kind dot string of that. Yeah, we know that this value is comptime known. Right. Value dot, oh yeah, this dot kind dot type dot unwrap. Yeah. And the type is basically int or string or enum or type and type never. just-in-time operation with stuff. Mm-hmm. Hmm. Sure. Also, yogurt fun. Oh. Okay. Okay. So the compilation compiles now at like writing the yogurt body. Yeah. A value is maybe true. Hang on, wait. Oh yeah, expression.pop is what we really want to write, I think. Yeah. What? It compiles. Wait. Oh, this is the yogurt. The type of that is true. It's not in comptime, and the value is also comptime. It's true. Yeah, I guess that's nice. How about what was it? Main? Oh, main int. You know, main int. So the t got turned into an int. That's cool. So let's say I basically call built-in add. You know, this with ints, with stuff and stuff, a double int, like this maybe. Multiple functions match main int. Well, that's unfortunate. Do they though? I mean, there is this. What? Multiple functions match main int. Oh, name matches. No, full matches is what we want to do here. Yeah. Okay. Find function built-in add. To do. Oh, right, because function calls don't work yet. But still, that's pretty cool. Find function built-in add. Let's do that, because I think we can actually do that. Yeah, yogurt. Yeah, find function built-in add. So what we need to do here is we take the arguments, we take their types, and also the comptimeness of them. Okay, so in the egg, you can't really call an enum, right? I mean, I think you can, but you have to do that directly. You can't. Oh. I mean, you can't do this, because this looks for a function. Foo. You know? So you have to do it like this. Which I think is fine, because this has to be like known, this value. If the type of this is like foo or bar, you know, then you can't call it like this anyway. Okay, so yeah, start. Actually, how does that work? Like if we, oh yeah, we don't have calls yet. If we have a, I mean, let's just implement a switch. We switch on true. If it's true, then we evaluate to 2, otherwise to 3. This, what does this compile to? Ah, thank you. Thank you. Handling fonts, but that variant doesn't exist. Okay. That is... I think I don't get it. What's going on here? Oh, right. I mean, that actually makes sense, you know, this is just true. If this is a bool, then sure. Yeah, actually, let's just for testing, let's compile the main function for something else. So we look up main. Yeah. Let's just call it with an enum type that maps true to, you know, an empty slice. Yeah. And false to an empty slice. Ooh, okay, so there is no function named main for the args true or false. Oh, well, that's actually true. That's like, yeah. Now this should work. Yeah, there's the main function that accepts true or false. So now we switched on a non-enum. Ooh. We did not. weird. Super weird. Yeah, and just give it a condition type. Int. Oh, is that like hard coded somewhere to int? You say lookup and then, oh yeah. I guess let's just compile this to the argument as a bool. Okay, this compiles. I mean, that's pretty cool, right? We have something that's okay, wait, can we say, ooh, yeah, can we say this? No, I don't know, this evaluates to foo and this to bar. What's the type? The type is foo or bar. Sure. Sure. Yeah. What if the stuff was comptime known? You know, known at comptime. So yogurt a value, yogurt value with the type bool and the kind yogurt value kind dot enum containing a map containing this, but with yogurt values instead of yogurt types. Oh, yeah, there's a tag. Yeah, I know. Tag containing a tuple. We know it's like compile time known to be true. It doesn't really change anything. Okay. Oh, but it's not an error. No. See, this is still like it's valid that both branches exist. And actually, let's edit the code so that in here we call, I don't know, not stuff. Yeah, we switch on not stuff, and not is not accepts a bool, returns a bool, and it's basically just, you know, switch on the bool. If it's true, return false. If it's false, return true. To do find function not, yes. Yes. Now the question is, what are the types? Let's just implement the lookup. Just is doing a lot of work in this sentence, but yeah. Let's say we take the arguments, a list of yogurt ID. We take their types. Yeah. We have the arg params, which will be a list of yogurt param. And yeah, and we basically do this. We look up the argument. We get the type. And we get the like arg params you know, basically if the argument, if builder.get the value, if that's some comptime known value, then this will be yogurt param dot comptime value, else it will be a runtime value of that type. Oh, wait, what? Oh, like this. Yes. Okay, so then we have args, argtypes, argparams, argtypes, argparams. Okay, next we will look for the receiver. And we will basically just do egg.lookup. Compiler egg. Yeah. Dot lookup with a string, correct. And it also needs the slice of yogurt types. Right, because the overloading, the lookup, only depends on the argument types, not on like whether some of them are comptime known. Okay, and then basically to do implement calls further, and receiver should be like let's print the receiver dot dot debug, why not? And also the call receiver and the arg params and arg types. Basically everything. Ah yeah, but of course the params can't be written, so let's maybe debug them. Sure. Okay, yeah, implement calls further. We want to call not with, well, a comptime known yogurt value of the type true or false. And what kind of value is it? Well, it's basically the true variant with no payload. The type of that is true or false. And turns out that works because, you know, we look for a function matching true or false. So we find this egg fun not accepts true or false, returns true or false, and you know it has this egg code inside, sure. And basically now we want to compile that function for this comptime value. Nice, very nice, I have to say. Yeah, I'll take a short break and then we'll get back to this. Okay. So, yeah, implementing calls. Yeah, we see the correct function here, which means this actually works. Now we only need to specialize or compile that function for what is it? Specific params, which we also already have, and we have the name. We can just do that. Hang on. What is it? Let's call it maybe fun. Yeah, and fun dot to yogurt. With yeah, sure. Yeah, this call doesn't work. There is only to yogurt with a slice of yogurt params, which is in our case the arg params. We have the name of the function, which is call.receiver, and also anything else, egg and yogurt. Yeah. Oh. Compiler.egg and yogurt. And compiler.yogurt, I guess. Yeah, that, down here we should do something similar, I think. Actually, let's look at what we did down here. So we switch on something, okay, sure. We switch on the receiver type. Yeah, I don't know, we don't really need to do that, I think. But okay, yeah, we have this, then the return type, which is just compiler.eggdefs. Okay, yeah, we get something, and built-ins are handled up in the yogurtfun.toYogurt, eggfun.toYogurt. So we know this is a function, and we should check that that the amount of arguments matches. That's already happening in the lookup, so we don't need to check that. Oh yes, and this is what I wanted to see. So fun.toYogurt with the arg types, in our case the arg params, because we want to like compile a constant fold. Then the function name, the compiler egg, compiler yogurt. Yes, perfect. Exactly what we want. And then we have the return type. An egg fun. Oh yeah. Oh. Like this. Okay. Yeah, and then we can just commit yogurt opt.call. Do we need to? No, we just return that, evaluate to that. Yogurt opt.call with a receiver, which is not in scope true, because this should be like an, I'm guessing like the signature or something. Yogurt call. Yeah, yogurt call has a oh no, we don't want that. We want a yogurt signature to be here. We don't have like closures or anything like that. We just, yogurt signature. Oh, well, never mind. Yogurt signature of the function name, which is call up receiver, and actually let's like we've accessed that so many times. Yeah. Yogurt signature takes the name and the params. Yes, like this. Okay, yeah, I like that. That's basically it, and it's a return type. Nice. Yeah. And I mean, in this case, like currently all function calls will happen at runtime. But we should, of course, like propagate comptime values further. Ooh, yeah, you see here, there is call, not true. Nice. And then that means that we compile not for true. Oh yes. And if it's true, then it's this. If it's false, then it's this. But the type of that is true or false. Okay, like we should comptime optimize this, I think. Yeah. Yeah, we want comptime values to be propagated further. Basically, where does it, like the cast, for example, it should also still contain the comptime value if the other, the cast thing is comptime known. Yeah, it was like with the common type, and then we had cast expressions, and basically, yeah, these have the common type here. And I mean, yes, that's true, but we still want to have the concrete value. So we want to have a yogurt value where, sure, the type is the common type. Yeah, but the kind is... Oh, no, actually it depends. It depends on whether the return thingy is comptime known. Yeah, case value, I think. Case extra, something like this. Yeah, and then the case type is just, you know, case expo dot type, sure. And for the new returns, you basically switch on case expo, and if that's, on the value of that. Basically, if the value of that is some value, then we do this. Else we just push this with the, it's runtime thing, you know? Yeah, yogurt up.cast. Yeah, builder.push yogurt.up.cast with a old body.returns. What? Yeah, we don't need to cast this specific thing. We can just say, well, this is a comptime known value. The kind is yogurt value kind dot something. Oh yeah, just the value. Oh man.
Oh, this is not like completely correct. Because we don't just want to adjust the outer type, we also want to basically
reverse down the value, I think, and adjust the types of the intermediate thingies in there, but okay. Yeah, so this is now comptime. No. Yeah, this returns false. Cool. Very, very cool. Still wondering if we can somehow simplify that. What? And I think we can. You know, like. Yeah. Let's simplify this. Okay, so the thing the thing that bothers me with this approach is that things are just so complicated. You know, you have like what parents, and you have these values that you sometimes attach to them. Sometimes you don't have values, but you have like types, and all of that needs to work. And the foundational issue is that you have these complicated, like, you know, operations. That each expression now is an operation and a type and an optional value. That's like so much state in there, and all of those need to line up, and you need to basically, with each operation, like with each egg thing, like a function call or a switch or something, you need to think about how does it affect the operation, or it probably just creates new operations or something. How does it affect the type? How does it affect a comptime value? And it's just a lot of stuff to keep around and keep organized. So I think I'm actually gonna remove the value from here, and instead, in this comptime thing, add the value. That's like, that feels natural, doesn't it? That you can just say, I have this comptime value. Like, of course that makes sense. Of course. Yeah, I think I like that. I think I really like that. Yeah, and then this right here, you know, it just has, yeah, an operation and type. That's fine. Does that break things? Well, of course. Yeah, associating an operation with a value is no longer something that we want. Yeah. Do we want this parent? I don't think so. I think based on, you know, like, yes, this is definitely useful, but for a value we may want a toOp that you can call, you know, on a yogurt value, and it returns the yogurt op, even like yogurt expert. Which is just yogurt op dot comptime with the value, and the type of that is the type of the value, something like that. I think something like that we can also implement for the parameter, where we basically switch on the parameter and then do different things. So if this is a comptime value, then we just say value.expression. So basically we replace a comptime value in there, while, well, if it's a runtime thing with a type, then we do something like this, where the operation is a yogurt op.parent. Yeah. Yeah, and then these are just parent.get.to expression. We push this expression to the builder. And oh, what's here? For the value. Yeah, right, that doesn't make any sense. Oh, does that fit as well? Of course it does. Clean. Okay, yeah, here we have, you know, this is super verbose, I think. Doesn't make sense to write a helper for that. Maybe, right? Maybe. Yeah, let's do that. Let's also create a helper like yogurt int, which takes an int and produces a yogurt value, and it just says, well, I'm a yogurt value, my type is yogurt type.int, and my kind is yogurt value kind.int of that int. Like, yes, this is a lot of boilerplate. And similarly for the symbol. Yeah. Type is, you know, yogurt type.enum with a map from the symbol to an empty slice of yogurt types. And the type is just a tag with that symbol and an empty slice of yogurt values. Yes, like this. Okay. Yeah. I like that. Yogurt type. Yeah. Also like yogurt type ordering is just, well, oh, this can be a variable. Yeah. This can just be yogurt type.enum with a map where less maps to an empty slice of yogurt type equal and greater that they do as well. Nice. I like that. Cool. Cool. So let's simplify this, you know? The value is just a yogurt int converted to an expression. Boom. Oh yeah, we probably want to do the same for strings. yeah, maybe call it yogurt value int, yogurt value string, yogurt value symbol. Yeah, this string means that these are all strings. And finally we have the yogurt value type, which takes the yogurt type and it returns type, like basically the type of that value. Comptime, no? Okay, yeah, yogurt int, there was no yogurt value int, yogurt value string, nice, yogurt value symbol, nice, param is unreachable, switch, we have the condition, yeah. So in here we just say case expression. Oh yeah. If this dot up is comptime value, and then we just push yogurt value, convert it to an expression. Else we push a cast expression to that common type. Yes. Yes, 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 that's nice. And for a call, we basically, we don't do this, but we check is this comptime value, then this will just be param.comptime. Nice, nice. And param, well, no, we can just say this dot to expression. And in here, for the builder, we can just check, hey, is this a comptime A or B? And then we push a yogurt value int of this. Oh, right, value converted to an expression, of course. Yeah, and here we basically do the same thing to check is the operation, is it comptime? No? Well, then we return this value converted to an expression. And oh, this is just a single symbol. We have a helper for that. Yogurt value symbol of the symbol. Boom. Okay, this is beginning to look nice. And this, of course, is the yogurt type ordering. Oh, like this. Nice. Yeah, if the operation is comptime, then we just take a yogurt value string. I mean, who would have thought that writing some simple helpers can simplify things so enormously. Okay. Yeah, and here we basically, oh yeah, we say the op has to be comptime, or, yes, beautiful. So this right here is just, yeah, for now it's that. Yeah, I mean, we will refactor this when we support enum fields and stuff like that. So then again, we can, yeah. Let's simplify this. Cool. Yeah, this looks reasonable. Ooh. 94. Expression dot, oh, true. Yeah, we don't do that anymore. But if it's a comptime value, then we just write the value right there. Which makes sense, you know? Boom. Wow. Okay. Okay. Yeah, like these, you know, before we had some casts here and crazy things, but we don't even need them. If, like, these can be completely detached from each other because this is a comptime value, you know? It doesn't, we don't need to cast anything here. Okay. I like that. I really do. Okay, so now let's do more comptime stuff, I would say. If we have a switch and this is comptime known, then, well, let's check. So, oops. Yeah, we have a switch and it's comptime known. And we have the condition type. Question is, do we still want to do this? Do we want to lower all the branches? And I think we don't actually. Nope. Nope, we don't. We just want to yeah, basically oh yeah. Yeah, we can check this in any case. Make sure all variants are handled and no extra variants are handled. Because that's basically what we do here. And yeah, this is the other way around. Like we take the variant in condition variance, then the switch dot cases dot contains yeah. Okay. You don't handle, or rather, like, you switch on, what's the condition? You don't handle the okay, cool. But you system okay, yeah, so then this happens, we can just unwrap this here, but this, we only do this if it's not comptime known. What do we want to happen if it's comptime known? I think we just I'm not entirely sure, to be honest. Yeah, let's just special case this. So if the condition expr is this, this is what we are currently doing. We check that as well. Okay, so if condition expr.up is comptime value, only compile the corresponding branch. Otherwise, we want to lower all cases. Oh yeah, we want to check this actually. Yeah, let's do it like this. So for each case, we want to check that the corresponding variant, aka condition variance dot get case key is exactly this, and case params is case dot value cases. Yes, and we want to check that the variant args len equals the case params dot len, or we panic. Are handled. The no extra variants are handled. Number of parameters for this case match the variant args. Okay. Okay. Nice. Yeah, len is not a field on case body, that's true. But on like this, we can do this. As variant args of len that you bind case params to len. Cool. Yeah, lower all cases. Get maybe unwrap is equivalent to just get. Nice. Yeah, this can't, like we don't need to check this because we already did above. Yeah. Yeah, and here we basically, what we want to do is we want to not do this, but instead we know the value is a tag, and then we want to yeah, we know this is a tuple with the symbol and the arguments. Oh, right. The kind of that is a tag, like this. And then we basically want to get the corresponding case of that symbol. We know that exists. And then we compile only that. Yeah, like this, case.toYogurt on a builder. No, not quite. I think. Nope. No, we just want to. Yeah, we basically need to handle the case if there are parameters. Maybe we won't do that right now. You know, like if tag.b.len is not 0, then to do handle comptime switch with case args. Stuff like this. Yeah. And then we just want to lower the case. Yeah, similar to how we call toYogurt on. Like, how does that work? We have the parameters, sure, But then we'll just create expressions, you know, and we'll just add them to some body. That's essentially what we want to do. We just want to do this. Yeah, the case dot value, I think. Something like this. Yeah, this is an egg body. Ah, yes. And then we say, well, please convert this to yogurt directly on, you know, like our builder. Builder. Oh no. Yeah, I'm just realizing something. Like we have the, you know, we take this expression, and then we compile it to yogurt and add that expression, that resulting expression to this expression list. Now what we do in this case is we basically want to like insert the switch case, the matching switch case, right there in the body. So actually we need a way to like add things to this list. That's kind of ugly, I think. At least in the current design. Well. Stop push. But that would be super cool. Actually, you know what? Let's... Yeah. Oh, this is kind of... It's kind of nasty. Okay, yeah, I guess let's postpone this right here. You know, just comment this out for now. Yeah, case is not in scope because sure. Okay, so we call not true. Yeah, let's maybe like focus on something else first. So, question is on what? What do we want to focus on? Maybe getting it to work, including the rest of the compiler pipeline first. Sounds like a reasonable idea. So here we implement plus for takes two ints, produces an int, calls built-in add. Yes. Now let's call this from the main function. Let's say the main function accepts an a and it calls plus AA. And let's just see what happens when we type check this, but of course we need to look for a function that accepts a yogurt type int. And then we compile that for not a comptime value, but a runtime type. Okay, so yeah, we can see that we have the main function that takes an int and it calls plus with that argument. Okay, and now I want another function that can add to strings. A is a string, B is a string, produces a string, is defined as built-in concat of A and B. Okay, yeah, it's not chosen right here, but it would theoretically work. And yeah, we can kind of test it like this. Hello world. Called none.unwrap. Okay, I mean that's not good. So what's happening here? We call plus with the argument, sure. We have a string hello, string hello world, and then we want to convert that to yogurt. Like, first of all, this seems fine. This, like this up here, the egg, beautiful. Called none.unwrap to yogurt body builder. On a built-in. Built-in. Yeah, I think that's probably this right here. Ah yeah, where we say this should be a string. Okay, this works. Cool. Yeah, and we can also see that this results in this in a comptime string hello world, and we just return that. Nice. Yeah, so here we call hello and world, and that works. Yeah, before we optimize anything and go into more comptime stuff, let's just finish the rest of the compiler pipeline so that everything works and we can run those programs. So converting to C. Yeah, we have this collecting of types, you know, with the yogurt types, all that fancy stuff. Now comptime int doesn't exist anymore. Comptime string doesn't exist anymore. Fun doesn't exist anymore. True. But we do have a type, and we have the type never. Oh yeah, we already do down here. Let's move that up here. Okay. So then comptime int doesn't exist. Comptime string doesn't exist. Yeah, fun doesn't really exist. Type does exist. And I think type will just type new and collect types. New. Yeah. The type will contain nothing, I think. Because those should only exist at compile time, right? Well, at least after, like, removing unused code. Op for operation, right? Is it fun.code.get? Nope. Yeah, getting a signature on fun, that's kind of weird. That's true. Oh, yeah, we already have the signature. The receiver is the signature. Okay, so when we cast something to an int, we don't actually need to handle that, I think, because it never occurs. Even comptime ints have int as their type, and you can't cast anything else to an int. Oh yeah, so this is unreachable. Same for strings, by the way. I think that code is still useful because it needs to be somewhere, right? Yeah. Okay, sure. Let's just compile this and see what happens. Wrote code to test.c. Let's see how horrible this code is. Yeah, so here we have the main function that accepts an int. And it has type int. Oh, I see. I see what's happening. Yeah, if it's a comptime value, we basically need to switch on the value. You know, if it's an int, well, then we need to assign that int. We need to say where's that id here? id.mangle equals int. Something like this. If it's a string, now we basically want to do this. So we set the data, we have more indentation, we set the length. Yeah. Value.kind is the thing you want. You don't handle type, true. So if we have a type, yeah, we don't actually like do anything. Types don't. Is hopefully not access the runtime. If it's a tag, well, ooh, now we need to look at the type and see which index that thing is. So basically this right here. Right, the target variance. Yeah, that must be an enum with variance. Variance is expression dot type dot enum dot unwrap, and then for each of those variants we want to see if the key is the tag dot a item.a, because it's no, that's kind of weird. Wait, for each this is also called tag. No, for each variant we want to check if the variant item key equals tag.a, then target index is variant.index. Yes. And then we just want to say that, yeah, basically this, except not in a case, but just unconditionally. Yeah, we just say we set the tag to this index. That's it. Okay, let's have a look at the C code. Okay, this looks much better. So we have the main function, takes an int. So then we have this, type int. We call add on that. What does that do? Well, it calls built-in add, which is defined down here, and it just adds those two ints, returns the result. Sure. And then with strings, another string, we concatenate those strings using this function, built-in concat, which just creates data, hello world, concatenated, length 11, and returns. Nice. Cool. Very cool. Okay, so I should probably commit something to GitHub just to Git just to be safe, because we have so many changes here. Basically we implemented most of the compiler pipeline, We thought about how types flow through the toast definitions. We have an expression guided graph where we kind of have type resolution, and we place type aliases with the pure structural types that are contained, and we have lots of code of handling that. And then in the yogurt things get even more crazy, where we can look up functions based on type, and yeah, basically having this overloading implemented. Okay, yeah, that's a lot of code. So let's maybe implement a new type system. Seems reasonable enough. Okay, so what's next? Before we do any more comptime stuff and compile time evaluation and whatever, I just want to fix a few things. So one is, okay, so I want to concentrate on the one thing why we changed the type system in the first place, and that was recursive functions. So I want to because the thing is, we don't really need recursive functions unless we also have recursive types. And that's something that we can't do right now. But in order for the language to work, we need recursive types. So let's like maybe check, let's just check where things fall apart when we have recursive types. Let's say we have a linked list, you know, a list, linked list of t that's either like it's either empty or it contains more. So more t and then another list t. There will probably be an infinite loop in the compiler somewhere. Let's see. Yeah. Yeah. Oh, and an overflow. Okay, with a long stack trace. But we know where the overflow occurred, so when converting a toast type to egg, at some point we are probably out of memory and then things crash. Yeah, because this takes an infinite amount of time, which is generally not something you want. Well, okay. So I guess toast to egg. We need something new in our egg type actually. Because remember, in the egg, types are resolved. We only have completely structural types. There is no such thing as list of t. You know, there is only like an enum of either empty or more of some t. And hang on, what is t? Well, t is, you know, either this or it's or it's this, and so on. So this basically is like an infinite type. And we need a way to represent those recursive infinite types. Yeah. So how do we do that? Because the cool thing about the egg was that types, you know, that no longer have names. In the toast, everything works out because here a type can also be a call and basically say, well, I'm like this other type, and this can be recursive. So a type can basically contain itself. But in the egg, like that doesn't work. There is no call anymore. All of the calls got resolved, or they, like, currently they take an infinitely long time to resolve. Right. So how do we deal with this? I think the easiest way would be to, I think the most elegant way actually would be to have some sort of extra type in here, like recursive, and then it tells you how many egg types above you basically need to start to how far above you need to start reading to like continue traversing down this path. And let's maybe draw some stuff. Because the thing is, infinite types, they make things a little bit more complicated, both in the like overloading, like when we try to find matching types, we need to basically be able to compare infinite types. We need to be able to work with them, to, like, if we switch on an enum and that has an infinite type, we want to traverse down there somehow. So yeah, basically I think you can represent types as trees.
you know, you have a type, I don't know, map or something, or in our case list. Yeah, I guess let's just create a new layer. We have a type list. Let's just define a list of t. You know, it's either empty or it's more containing a t and recursively a list of t. Then basically what this becomes is, you know, like an enum time, like this. This is a pipe, by the way, with multiple variants. There's the empty variant, and then there's the more variant. The empty variant doesn't contain anything. The more variant like actually contains two more things. It contains, you know, let's maybe put in an X in here. There's nothing there. And the more variant, it contains a T, which, you know, can, this is not a concrete type. It can still be specialized to some T. Yeah, either it contains a T and a list of T. What I'm proposing is that here we basically say, well, this is a recursive type, however we like represent that. And please start like two levels up. So then when you traverse down in here, you're actually then starting over at the top. Yeah, and I think basically whenever we like traverse down into a type, we need to take that into account. Because like let's say you have a type, I don't know, a type that is either foo or bar. And the bar variant contains, I don't know, like let's say foo contains an int and bar contains another enum that is either A or B. Yeah, actually, let's use short names for all of them. So we have either A with an int or B with an enum, which then is either C or D containing a foo. You know, like this is a valid type, of course. If you were to convert this into a tree, you would basically have an enum that is either A or B. The A is just, you know, an int. And the B is, well, another enum that is either C or D. Yeah. And if it's C, then it contains nothing. If it's D, then it's basically recursive. Up here. And now the question is, like, assume you switch on this foo, and then you are in the B variant. And you're like, okay, now, I don't know, I have a foo, and then I switch on that foo. Now, if I have an A with an int, I do some stuff. If I have a B with bloop, I do some other stuff. The question is, what's the type of bloop here? Because you can't just, you know, basically I want these to be defined over how many layers up they go.
because then I still don't have any names in them. But that would basically mean that this is like a recursive type of 2 or something. And then the block type, well, the type of that would need to look something like this. You know, it's an enum with either C or D. C maps to nothing, and D maps to another enum containing A or B. Yeah, and containing A or B. Yeah, and A is an int, and B is recursive type that points up here. So my point is that when you traverse down into types using like switch, or later on when we have structs also just like field access, there may be recursive types that point to, you know, the beginning of the type that you now traverse down into, and you can't just leave a type down there that says, well, start 2 layers up, because that layer doesn't exist anymore. So then you basically need to traverse down, but at the same time extend the type down there, so that basically that, you know, that the type basically wraps around some way. Yeah. And also, like, joining types, maybe that gets really difficult as well. Like, assume we have a type that is like guaranteed, basically an enum type that is guaranteed to only be foo, and another enum type that is guaranteed to only be bar. That works, yeah. And you can join those to an enum that is either foo or bar. But now consider this: the foo variant also has a payload, and the payload is also, the payload is bar, which then contains like a recursive type, you know, that basically starts here again. And actually let's say that this right here is just foo. And it also has a payload that tells you, well, start here. Do we want those types to be joinable? I actually think so. You know, the type of this, like if we look at the top level, they both only have the foo variant. So the resulting enum should also only have one variant, foo. But then the next variant can be foo or bar. So this down here can be like foo or bar. Another question is kind of, well, you know, if it's foo, if it's foo, then we are definitely in this case. So then we want to start, you know, foo with basically a pointer to up here, or it's bar, and then it also has a pointer to up there, I think. Yeah, because you can never have 2 bars in a row. But you see where this is like weird. I mean, maybe let's draw some trees. So we have our enum, that, yeah, I'm gonna remove the circles around that. Makes things more cluttered. So yeah, we have an enum that is, only has one variant, foo, and that variant contains another enum. Now I like the circles. Well, that is bar, and it basically just points you back up there. And this right here would be an enum with one variant, foo, that directly points you back up there. So then when you join these, basically you get this, like this node and this node, they can be joined because both variants, they can be joined if both the variants are compatible. So in here we have an enum, and it only has one variant, foo. And then in order to join those types even further, we basically have to join these types, because here we follow the child, and here we follow the child, and then we want to join those types. So yeah, we want to basically join this, traversing down basically results in this type, an enum with a bar that contains another enum with a foo that then is recursive. And we can join those two, that works. It's because they have different variants, foo and bar. And the foo variant, oh right, I see it now. In the foo variant, we'll just take this, if it's foo, then actually we definitely know that it came from this branch of, when you have a switch and you join these two types, we know it came from this branch. So we know that we are basically stuck with this recursive type that only ever has foo variants. And if it's bar, then we basically want to oh yeah, if it's bar, then we know we are in this type. True. So then this will be the resulting type. Let me, this is not it, definitely not it. You see, this is not intuitive what comes out of that. It totally makes sense. Like this is, let's see. Oh, come on. It's an enum type with only one variant, foo. And that variant contains another enum type with two variants. There's the foo variant, which only ever results in itself being called. Yeah, something like this, which starts here. And there is the bar variant, which then contains a payload of the foo variant, which contains a payload which only ever calls this bar variant again. Ooh, yeah. Right. Wait a minute. This is not even correct. Because once we're in this bar variant, we know that from now on there will always be bar and foo alternating. We know that we can't ever go into this loop again. So this is actually wrong. Once we have bar, then we have an enum that only contains foo, which maps to an enum that then maps bar to that. Yeah, you can't map to a single variant in here. You have to foo, which then has an enum that can only contain a bar with a payload, which then maps to this enum. Yeah, that's it. That's the resulting type of joining these two types. Yeah, this will be fun. Oh god. Like you think, you know, like structural typing, sure, let's do it. It's simple. Well, then you join recursive enum types and oh shit. Okay. This is fine. This is totally fine. Like, I would not have thought that like joining these two types would have resulted in this mess, in this, like, what? Wait. Yeah, and that's not even correct, because this is a foo, and that contains another foo. Right, we have 1, 2, 3 foos to like traverse down here. So we have a foo, yeah, because from this point on we could also reach a bar again. That's not what happens. Instead we have a foo containing an enum with one variant foo, which then maps to that same enum. Yeah, that's the textual representation of this tree. Yeah. You know, that's fun. That is super fun. Yeah. Can we, you know, when we compare types, can we do that efficiently? I think we can, because for each type we can basically have like a canonical representation, like the minimal tree that represents that type. And we can then just compare the trees, like, you know, like a literal comparison of are they the same tree. Okay. Oh, that's the maximum. Well. Okay. Yeah, maybe let's remove that thing up here. And just move everything to the top. I'm just wondering if you have your list type, you know, it's an enum that is either empty with nothing inside, or it's more containing, well, two things, containing a t and yeah, basically the same enum. But what if you have a tree that looks like this? You know, basically here the same list definition is like, for some reason someone constructs a more with an empty or something like that, you know? Or you have a recursive function that adds 2 elements to a linked list at the beginning. then you basically have more of a recursive call. And you would probably end up with something like this. I mean, at some point there will be a recursive type, but this is not a minimal tree. And I think in order for us to be able to compare trees efficiently, we need to be able to reduce trees to a minimal version. Yeah. Let's maybe maybe we don't need that straight away, but later on. And we can definitely implement some of this already. I'm not sure, like, even how to do some of these things, but I guess we'll figure them out as we go along. Yeah. So yeah, I'm gonna switch back to the PC, and so here we have a recursive type, which is basically the thing that tells us start like some this many levels further up in the tree. Yeah. Yeah, recursive type. Oh, how are they? We could just do like something like recursive with a level, and it's this. Sometimes I don't know where's the tick. It's this. Okay, yeah, this evaluates the string true. Okay, so yeah, this is how we'll represent a recursive type for now. Like later on, we will, probably have to do something a bit more user-friendly and understandable, but well. Okay. Do we want like type a separate file for type algorithms or stuff like that? Because I feel like they have very they can get very long. I'm not sure, but but I mean, we have this in here as well. Yeah, let's just, be like, hey, let's type algorithms. Turns out some of the things we want to do with types are not trivial because of recursive types. For example, joining a type that only contains foo, which contains bar, which contains, I think it's like this. Yeah. Something like this. And a mess. Yeah. And then we have like types. Foo containing a bar, containing the type that is, it doesn't like map to the enum, but to this enum, so it's like 2 levels higher. And the other type is foo, just with 1 level. And here I'm just gonna say, well, this is, by the way, this is foo containing a bar, and containing a foo containing a bar, containing other stuff. And this is foo containing a foo containing foo containing a foo containing other stuff. Yeah. Joint. That's like a foo of either a foo with some stuff or a bar with some stuff. And this is guaranteed to only ever be foo again, so something like this. And the bar is guaranteed to, from this point on, always be foo or bar. Foo and bar, like alternating. So like this. The joint type is this. The top level is always foo. The foo variant. And the level below that decides whether it is always foo forever or whether foo and bar alternate. Yeah. Oh, that also means our, wait, didn't we have a type joining algorithm down here somewhere? Oh, that was in the yogurt. True, that we don't need that here, I think. Maybe we do. Yeah, maybe we do. But we don't have joining types, we only have resolving types, basically. Okay, so there is the toEgg function, which works on a type and just converts the type using an empty map. And I think basically we need to pass in a recursion anchor, or like, oh yeah, we could also have like a type. You know, like we have this enum, which is always foo. No, foo is this that you can traverse down into, but it's always foo. And then we have another type like bar, which is a list of foo or something. And of course the list is not recursive, but the foo is recursive. So the recursive thing doesn't even have to start at the top of the tree. It can basically point to any part of the tree. So I think we need like a list of existing types that are further up in the tree, maybe, but not the fully resolved types, but the names and how those types are called, if that makes sense. Yeah. So yeah, I'm gonna take a quick break. Okay. Yeah. So we basically need like a list of named types maybe that we have called. yeah, and how deep we currently are inside of those types. So basically like parent calls. Yeah. Yeah, I like that. I like that. And basically this just tells you parent calls and the depth that we currently are in. And the parent calls is just a list of I think tuples of the like an int maybe. Yeah, and an egg type call. So an egg call, hang on, this is, oh, egg call is like a separate type, right? Maybe not. Oh yes. No, that's not the type. Oh right, it doesn't exist. The toast call is what I'm thinking of. Yeah, toast type call. That's it. Yeah. Oh yeah, but this is not okay. Let's say this is a tuple 3. Now we have a struct ongoing type call that saves the depth, the name of the type, and the args, which is a slice of like egg types, fully resolved egg types. Does that make sense? Yeah, I think that makes sense. Okay, yeah, and this is just a list of ongoing type calls, and we have our own depth. So this will be an empty list in the beginning, and the depth will be 0, and then basically in here we have a variable. Okay, just return that. We have a call. Now things get interesting. Things get really interesting. If this is one of the fundamental types, okay, fine, handle those separately. But then if it's like actually a user-defined type, yeah, we basically have this. Where do the args get compiled? Oh, here's where that happens. Okay. Yeah, call.args.iter. Let's maybe lower the args first. Yeah, so lower the args to egg types. Basically by doing this for arg in call.args, do args.push, arg.to egg toast and parent calls and depth +1, I think. Then we have the arguments. I mean, we can also like do that outside of here, because why not? Lower the arguments. Well, actually, we can do that even before we check anything, because later on, if we have built-in types that also like accept arguments, you know, we want to reuse that logic. So yeah, lowering the arguments works like this. Yeah, that's basically it. So then, yeah, args is args to slice. Sure, let's do that. Handle built-in types. Look for custom user-defined type with the name. And basically, instead of using call args, we'll just use the args. Yeah, and here we can just say that. Right, why does this not work? This is, oh, right. This needs like parent calls and the depth, which is calculated +1. Wait a minute, is it actually +1? Yeah, I think the arguments. No, I don't think so. Because type, you know, like calls, they disappear. They don't wrap anything with types like automatically. Yeah. But the idea is that in here we basically push something, the ongoing type call to the parent calls. So here we know the, you know, sure, the depth, we have that. The name, we have that. The, what else is there? Depth, name, args. Right. Yeah, args is, yeah, args, we have that. Cool. Actually, let's save the name as well, because why not? And then we can just say boom, this, clean. Okay, yeah. And then convert that, you know, var type is that. And then the parent calls dot top, and then return that. Okay, and now the cool thing is that basically we recursively lowering a type. If so, we need to insert a recursive type instead of, you know, like digging down or like into something like that. So the way we do that is we can basically look at the parent calls. And we check if the name matches our name and the call.args matches our, if they match our args, then we can just return egg type.recursive of our depth minus the call depth, because that will be the additional amount of layers that we are down in the tree. And then we only need to ensure that for each like layer we actually add 1 to the depth. So yeah, parent false and depth plus 1 in the enum case. I think we only have enums currently, right? That's the only way to traverse down. We have type variables, sure. We have calls, and we have, yeah, okay. We don't have a lot of types right now. Yeah, and in this, if a type in the enum says, hey, I want to be the type 1 level above me, it basically wants to then be another instance of the enum. That makes sense, I think. Okay, yeah. Very, very cool. So yeah, let's just try this out and see what happens. Oh no, you can't compare egg types. Well, true. Which means we can't do this. Yeah, but I think you should be able to compare egg types. Yeah. Question is, where do I do that? Probably just here. We have an egg type. Because, there may be some things like this assumes that both types are like normalized and stuff like that. So it just checks if they are the exact same tree. Right, so we want to switch on the type. And if it's oh man. Okay, so if it's a variable, then we check is the other type of variable. Bar. If b is variable var b, then var a equals var b, else false. If it's an int, we basically just return b is int, I guess. Like this. Oh. Yeah. B is string, B is type, B is never. Again, there's not like joining types or anything like that, it's just making sure that both types are the exact same. Yeah, so if b is an enum b, then stuff, else false. So what do we do here? We have two maps. I want to compare if they are the same. Wait, is that supported? Maybe it is. Hopefully it is. Yeah, if it's a recursive type with level, then we basically want to check if b is recursive with a level. Are the levels the same? You don't handle stuff is assignable to. And yogurt water. Sure. Oh, yeah, that makes sense. I mean, yeah, I guess for now let's just, you know, to-do. You can handle egg type recursive is assignable to map switch egg. case variant, case int, type, never, enum, which, oh no, oh, I see. Cool. Wrote C code to stuff, sure. And super convinced that this works. Oh, right, we don't actually use those types, right? No, we don't use the list. Okay, maybe this does work. Okay, that's cool. Oh, you know what? Let's actually not analyze, but look at this. So we have the toast, and here we just say, well, yeah, list t is either empty or it's more with a t and another list t. And then in the egg, oh, look at this. We have main, which accepts a list of int. So this, you know, it's an enum that is either empty or it's more containing an int and one above. Like one above means the enum itself. What? Okay. Okay, that's pretty cool. Like, I have to admit that's nice. That is nice. Cool. Cool. Nice. Wow. Just wow. What? Amazing. Amazing. A generic function that accepts a list, which is an enum that's empty or more of some t, and then it accepts an int and it returns a t. And this is specialized for list of int. Very nice. Very nice. Oh. Okay, but we can't actually use that type though, I think. So if we... Oh, how would we do that? We could maybe... Yeah, let's say we have a constructor called list that accepts an item t and returns a list t. And what it does is it just returns more of the item and an empty. I mean, this is cool. Yeah, this doesn't work. Okay. So, oh, expected equals, wait. Wait, what? Yeah, bacon is what we have, and then expected equals. Oh, yeah, this. Yeah, I can. Yeah. Oh. Ah, okay, yeah. Okay, so it fails even before that because currently we can't even like create enums. That would maybe be useful. So I want to create a maybe, for example. That is like a Rust option or Haskell maybe or something. And it's either some t or it's none. Man. I was just thinking, okay, maybe I should add a global sum method But then I realized that, well, you can just call sum with sum5, you know. I have to say that's, I like structural typing for this. Everything can be so concise and there is no way to mangle types into the correct, you know, to mangle values into the correct types, but it's a lot more fluid. It feels a bit more dynamic. And I think that combining this with static typing and comptime type reflection and so on, it's an interesting like an interesting exploration for sure. Okay. Okay, let's maybe what do we do? I think let's just make sure that you can create a maybe, that you can just say sum5. That's like everything I want right now. Called non-name symbol. Okay, yeah, so let's look at that. Oh, yeah, okay. I'm just thinking the git commits will be messy if we do this, but also have recursive types and stuff like that. But well, gotta do what you gotta do. Called non-name. Yeah, exactly. And the receiver is not a name but a symbol. Yeah, but that's fine because, you know, if it's a name, we do some stuff. If it's a symbol, we do some other stuff. Otherwise, we do this. And for, hold on. Yeah, we can do this either way. You know, like compiling the args. Sure, let's do that. And then in here for the name, we just push a call, while for the symbol, we push an add expression dot tag. Doesn't exist because, oh, yeah, because the receiver was an egg ID, and then in the yogurt, we would find out that this is actually a symbol creation. But in here, we don't need that. We can just, you know, have a separate thing already. So we don't need to special case that later on. We can special case that here. So yeah, we have an egg tag, basically. Egg tag, kind of rhymes. With a symbol, which is a string, and args, which is a slice of egg IDs. Right. Oh yeah, and we need to be able to print that and all that funny stuff. So here we have a symbol and we have args, which are the args converted to a slice. So let's maybe do that up here. Yeah, that makes this all much shorter and cleaner. Look how nice this is. Okay, yeah. This is not receiver. Oh yeah, receiver.name. No, we want to switch on the receiver and then. Wait, but receiver.name worked? Well, oh, it's an AND toast expression. You need to dereference that. Receiver is not in scope, yeah, because this is the call receiver. No, this, oh, sorry, receiver is, yeah, name receiver, like this. Ah, beautiful. Honestly, that is so beautiful. Wait, to nothing. Oh, because we, the code gets shorter and shorter and shorter, but it's, at the same time, it handles more stuff than ever. That's, I think we found a design, at least for the egg, that is pretty neat. Okay, so for a tag, we basically just write tag and then the tag symbol, and then we write the arguments like this. Nice. Yeah, we don't handle that in the yogurt. That is indeed true. Let's change that. We have a call. We have, oh, that's it. We have this call. Where does it end? Here. Okay. Yeah, if we have a tag, we basically want to do something similar, I guess. But like we don't need to you know, yeah, this doesn't even need to exist, I think. Nope. We can remove this and this and this, and instead we'll just do something similar. We have the args, arg types, arg parents, which we probably, no, we don't need them. So for each argument, we basically look that up. We look up the type and we push that to the args and the arg types. Okay, so far so good. Then we convert them to slices, I guess. Next we take a fun, no, we take a symbol, but that's just tag.symbol, so yeah, we don't have a function to call, we don't have a return type. Instead, we emit a tag, which is a yogurt tag with a symbol, which is the tag symbol and the arguments. And the type is just, you know, yogurt type dot tag, I think. Yogurt type dot, oh sorry, dot enum with a map from symbol to the arg types. Yeah, of course. Oh, and symbol is the tag symbol. Cool. Yes, cool. Args. I mean, we can't even inline that in here because why not? Okay. Okay. Oh, it compiles. That's good. Ooh, plus we have some int. That is nice. That is super nice. Nice. Okay. Okay, I can work with that. Wow. Yeah, let's maybe commit just that, you know? Symbol support. Yeah, basically like, hey, we now support tags, which is this. And in the, here we had to do these kind of things. Yeah, not that, this for sure. Not this, not this. Nope, 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 nope. Nobody, nope. Nope. Yes. Okay, yeah. Support tags. Okay, and next up, support recursive types. So let's say I have more, I don't know, list 5. Okay. I mean, this is most certainly not valid C code, but wow, look at this. Look at this. The type of this is more int empty. That's... Oh no. Yeah, okay. Yeah, let's fix that formatting, because why not? When formatting a call, we want to put that in quotes, maybe. Call. Because this can be like a complicated space containing thing. Oh, but not, yeah, no, never mind. Never mind. Okay, you know what, let's just have those in there, and we know that it contains no new line or anything like that. Yeah, that's what I'm looking for. So we call list of 5, and this results in more int empty. So we have more int empty. Let's tag more. Yeah, containing the 5 and the empty symbol. Nice. Very, very nice. Okay, okay. I mean, what's the C code that got generated? Holding this T is too nice, I can't even... Whoa! Okay, this is certainly something. Ah yeah, okay, it's just more of int and empty, which is what I expected and what makes sense, you know? Yeah, it has one tag, one possible tag. More. And it has a single union only containing the more variant. And then this more variant has 2 payloads, an int and an empty. And the empty is defined here. It only has an empty tag containing no payload. So this is like, yeah, basically non-existent. Okay. Nice. To do initialize tag, yeah, we can do that, I guess. C.mal to do, I mean, sure, but not now. Initialize tag. Oh, but you know, actually, not having that's cool. That's the reason that we realized there was something wrong here. Okay, so when we initialize a tag, what we basically want to do is, well, set the variant index stuff. Yeah, something like this again. feel like this exists like in 3 places or something. Yeah. So the expression, is it called expression? Yeah. Expression dot type dot enum dot unwrap dot iter dot enumerate gives us the variance of this type. And we want to see where is the key equal to the tag symbol. You know, then we set this global index. And then we just write, you know, like the ID. Is that in scope? Yeah. id.mangle.tag equals that index. And for each argument, so for each argument in tag.args, we basically write id.mangle.tag.symbol equals other stuff. Let's see, so we have the tag, and then we say of this tag dot as dot variant name dot index of the payload. So we need to also enumerate these. So such a nesting. Dot arg dot index with underscore in front. That is the arg item, which is the ID. Okay. Yeah, I think that works. That should work. Okay, so a friend of mine likes semicolons, and there is a custom error message for him whenever you do you write a semicolon in Martinaise. Yeah. Well, wait, what? Tag. Oh no, variant.index. Yeah, let's just compile this and see what happens. Okay, so hopefully it looks a bit better, I guess. Yeah, we want to initialize this more thing. And like obviously more has the index 0, so you know, we set that to 0, which is fine. And then we say payload 0 has to be this, and okay. So I guess the remaining things, those which don't work, is indentation, printing indentation, which yeah, like everywhere. Okay, we find the index, then we print indentation, we print the tag, and then for each line we print indentation. We set this to the mangled version of that. Yeah, it should be underscore 1, underscore 2, and so on. And we remove that. Oh, look at this. Nice. Like it. It actually has this to thingy, which is type more of int and empty, and then as is this union, and the more variant is a struct with an int inside and type inside. I don't know why this prints error type, but well, yeah, those get initialized. And then the entire thing gets returned. That's nice. Now the question is, how does it like deal with actually recursive types? Because it doesn't really deal with that. So let's say you create a new list based on the length of something, you know? So the main function gets an int, and it basically calls, I don't know, make list that takes a len and returns a list of ints. Yeah. It basically checks, is the len 0? If it is, then we just return empty. Otherwise, we return more with the len and a recursive call to make list with len -1. Yeah, we should add error reporting. Definitely. Okay, so something is not working. Well, what to do in this case? What to do? I think we don't support parentheses and expressions yet. So let's maybe turn it into multiple, you know, into like a tree of expressions like this. Basically that says the same, but okay, never mind. Maybe this is bad. Equals. I mean, yeah, doesn't it? Oh, I know. Same thing again. Same thing. Wait, what? Let's say I'm interested in the C code. oh, it's not used. I see. Okay. Make list of that A. Yeah, there was no function named equals, that's true. Can we use equal signs? Does that work? Expected switch condition. Okay, no, that doesn't work. Yeah, let's maybe define an equals function for ints. A is an int, B is an int, it returns a bool. You know, what does it do? Well, basically switches on built-in compare of A and B. If that's less, it returns false. If it's equal, it returns true, and if it's greater, it returns false. Okay, there is no function named minus. That's correct. I mean, now there is. Oh, but sub is not implemented, right? Yeah, I know. Okay, let's implement sub. To yogurt of a built-in sub. We get the parameters. If they are comptime known, then we just push a comptime known in by subtracting these. Otherwise, we add a sub instruction, and that's it. Whoa. Oh no. Oh. So we basically compile functions recursively in that case, right? Yeah. Look at that. Well, that's unfortunate. How do we deal with that? Well, I guess we will just have to, I don't even know. We compile fun, then we compile a body, then an expression, a fun, body, expression, fun, body, expression, fun, body, expression, body. Okay. So we compiled some expressions and bodies, probably in a switch, and then at some point we compile a function, which we already compiled. So that's not good. And this happens in the to yogurt. Yeah. True. I mean, you know, we compile this function to yogurt and then, yeah, we pass this yogurt in here. And we have this signature. Okay. Oh. Yeah. I think basically, we need to, yeah, we need to ensure that that doesn't happen, but that's pretty easy, I think, because this yogurt here is basically just a giant map of functions, you know. So we can just check, like at the beginning of the compilation. Yeah. We can just check this signature already exists in the yogurt map. So if yogurt.funds, you know, we get maybe that signature is some fun, then we just want to return that. And we don't need to compile it again. And that's like more efficient anyways, so it's useful that we do this. But then before compiling the body of the function, then we actually want to, you know, like input a placeholder function in there. So you got that funds.put signature, and then a placeholder function, which doesn't have the actual body, but everything else is correct. So it has the correct types, it has the correct everything, you know. Yeah, wait, but a yogurt function, wait, yogurt fun. Is it a struct? It's a struct. Oh, it doesn't even have any type information anymore. Well, I mean, yes, I guess that makes sense, because you can go to the body and be like, what's the, you know, what are your params, and you have yogurt IDs, and then you can look them up. So sure, that's fine. But that also means that in here we basically need to have a function with an empty slice of yogurt expressions. And the body is just basically like an empty yogurt body, I guess. What is yogurt body again? It's quite complicated. This. Okay, it has params, which for now, nah, no params here. Expressions, don't need that. Returns. Basically yogurt ID -1. Yeah, that seems correct. Okay, yeah, that's it. So, you know, we want to compile a function. If we have compiled this at some point, we're totally fine. And then we put this temporary function, should describe that somewhere, for a temporary placeholder in the yogurt. Recursive calls won't analyze the body, like the content. Anyway, they will just calculate the returned type based on the signature. Okay, yeah, and we need to make sure that this is actually what we're doing, because I'm skeptical. You know, previously we just looked at the last expression or something like that of the compiled function, and that doesn't work anymore. So yeah, we have this function. Yeah, exactly. So here we do this, but this doesn't work. Instead, we need to actually use the function signature now. That makes sense. Yeah. Yeah. So I think lookup. Yeah. This should not just return an egg fun, but also like a mapping from type variables to yogurt types. Yeah. So lookup result, egg lookup result, I don't know, contains fun, which is an egg fun, and an environment of like a type environment, basically. That's the way it's usually called in compilers, which maps the type variable names, strings, to concrete types, so to yogurt types. Yeah, and remember that we had this yeah, basically this, you know, this returns a map. A mapping, yeah. And this doesn't really work yet. Yeah, so I think we somehow need to be able to specialize types. And we did have like a 2 yogurt on types. I don't know where that was. Huh? Didn't we? Oh, that was before, right? Yeah, when converting the egg to when converting toast to egg. Yeah, that makes sense. Okay, so yeah, we'll just add a function specialize that takes an act type and an environment, which is a map from string to yogurt type, and it returns a yogurt type. And basically it's similar to what we do in, not in here, but in somewhere in here. Yeah, in here. Kind of. And instead of going from oh wait, yeah, egg types, they still have type variables. Yeah, they do. Okay. Okay, yeah, let's just implement that. So we have an egg type and we want to specialize that. And the way we do that is, of course, we switch over it. So we switch over the type. Yeah. And basically if it's a variable, then you know, if env.get maybe that variable, if that is some concrete type, then we just return that concrete type. Otherwise we return a yogurt type. Well, that doesn't work out. Yeah, otherwise we panic. I think that makes sense. Okay, so if env, well, var concrete equals this, or panic generic type not in type env, stuff like this. Yeah. Ah, weird. Oh. Okay. If it's an int, we just return yogurt type.int. String yogurt type.string, type yogurt type.type, never yogurt type.never, and now enum. Yeah. Right, we did that somewhere. Case string yogurt type string. What? I'm pretty sure we did that somewhere. Oh, here maybe. No, that's joining. But where does the egg type get converted to a yogurt type? That needs to happen. Oh, it doesn't happen yet, right? No, it doesn't. Oh, I see. Yeah. So when looking up type, when looking up functions, yeah, we just check, is this assignable to this? You know, is this what is it? Yogurt type assignable to this egg type, something like that. And then we find a matching function, but then we just assume the yogurt types of the call side as the parameters. We don't even, we only use those types for matching right now. We don't even use the type annotations in any other way. And it would be useful, for example, to ensure that the last expression of a function actually returns the promised type. That's something that we still need to do. And we need to, like what we do right now, basically, use the type signature to figure out the return type of the function, instead of looking inside the function body, which again, doesn't work with recursive functions. So yeah, for variants, we just want to, I guess, create a map from string to slice of yogurt types. And for variant in enum, we just do variants dot put variant dot key variant dot value dot specialize using our environment, and then we create a yogurt type dot enum with those variants. Recursive types just get lowered to a yogurt type dot recursive, which also should exist. But doesn't. Does it? It does. What? It does. Oh no, specialize is not used. That's why. You know, this is why you want tooling that works in isolation, even if a function is not used. Yeah, so where do we call specialize? Oh, right, when we compile a function call. Yeah, we have these, we have a call, and then in here, instead of looking into the function and getting from the function expression something and looking at the type, we just take the signature, return type, and specialize that. Wait, even before that, when looking up a function, yeah, here we want to return an egg lookup result, which contains both the function and basically like the type environment, which is called mapping here. Where we don't. Oh, it's a tuple 2 of these and a map from string to yogurt type. Sure. Sure. So this is the fun and and the environment. Fun and env. Here we push a tuple of the fun and the env. Okay, sure. So in here, this is fun and env.a. Env is fun and env.b. And now we have a lookup result. So now we can, in here, main, actually what we want is to return the main function, to turn the main function to yogurt. And in here, where we look up a function and then we turn that, we compile that function. Basically, we want to turn that. This returns the function like this, which is, by the way, not even needed, I think. Which makes sense, yeah, because we can't look at the function, you know. So we have that, and then we also want the result environment, the type environment, to use that to specialize the return type of the function. So basically result.fun, which is an egg fun, which has a result return type. We want to specialize that with the environment to get the actual return type instead of looking into the function. And now things don't work. Oh, but that's probably because now the specialize function gets analyzed and stuff doesn't work out. Oh, there is no still. Yeah, the specialize function is at fault. Why? Well, oh yeah, this should be string. Old habits. Yeah, dot specialize. Oh, we have a slice. What? Yeah, in 209 we have the enums, and then we say please specialize. Actually, I think this type is from the standard library, which you can also specialize, which allows you to reflect over Martinaise types, which, well, yeah, so specialize doesn't work because it has an, oh yeah, we should use the variant. Right. Oh, yeah. Okay. We need to have, this needs a slice, so basically for each of the arguments we have to push that in here. So that we can then call args to slice and add that to the variance so that we can then return the variance. Okay, yeah, and yogurt type recursive doesn't exist, which is what I thought, but it needs to exist. Yogurt type. Yeah, the model levels. Sure, but now other things don't work. Yeah, so levels, like recursive types, they don't work anymore. So we need to fix that. Okay. Yeah, let's just, why is this even here? If it's not used, that's, yeah, I don't, that's true. So yeah, also in here we want to be able to print the recursive type. Down here is an arrow where we join types. Oh, yeah. That's, I don't even want to think about that yet. You don't have a yogurt type.recursive. Ooh, true. So basically, I explained that those types wrap around, right? And we want a type to never be able to, when you inspect types using typeof and typeinfo and so on, you will never reach a recursive type, because as soon as you navigate into a type and inspect that further, well, the type will be extended at the bottom. So yeah, mangling types. Ooh, I haven't even how do you I mean, I guess something like this, recursive, and then the level. I don't know. Yeah, collect types. 71. I mean, you know, how are you supposed to do this? Right. Okay, well, what is going on here? Crazy. This is what? Okay, so we have equals. That takes an int and a 0 for comparing an integer to a 0. Okay, yeah. So we call built-in compare int 0, which is down here, which only has the compare instruction inside and then returns that. Sure. Yeah, then we switch on that, and if it's less, we return false, true, return true, false, return false. Okay, sure. So we basically create a bool out of that. But on compare, we looked at that, we have subtract of int and 1, and that basically just calls like built-in sub of int and 1. I guess. Then there is built-in sub, sure, which has the sub instruction, and then we have the main function that takes an int, and it calls make list of int. Which returns a list. So you see that this returns empty or more with an int and a recursive type. And that's correct. Yeah. Meanwhile, make list of int is probably the most interesting function here. We have a comptime 0. Then we call equals int 0 with the length that we get and the 0 that we just created. And then we switch on that. If the length should be 0, then we create an empty symbol and we cast it into this form, so it's either empty or more. Oh, I see. This is like a nested enum, which is just printed horribly. So it's either empty or more with an int and with this thing right here, which is again either empty or more with an int, and that's like recursive. Okay, and in the false case, we create a 1, and then we subtract the 1 from the length that we get in here, and then we call ourselves recursively. Oh, look at that. Look at that. Call ourselves recursively with the resulting length -1. And we can figure out that the type of that will be empty or more int. So we have recursive functions. What? That is amazing. That is honestly amazing. Wow. And then we create a more tag. The length, yeah, and the result of calling ourselves. And then we cast that to this type for some reason. Sure. Yeah. Oh, I see what's going on, yeah. So this branch evaluates to empty. And this branch evaluates to this right here. More containing an int and the result of that recursive call. So then when the enum only containing empty is joined with the enum containing more and an int and this list thing, the result that we get is an enum that either contains empty or more with int and the result of that list thing. That's actually correct. Yeah. It's just that, you can write this type more concisely by just removing this part at the beginning, because this is exactly contained right here in the part that is recursed over. But okay, yeah, so we need to minimize recursive types. And that also allows us to then trivially compare them. But okay, I like that. I really like that. Cool. Very, very, very cool. And I really like that even if you call a function with, you know, like completely comptime known values. Okay, that doesn't happen here anyway. Well, if you do that, you still get the more general type back. So you get an int or a bool or, you know, something like this. So you will get a comptime value, but the type of that will be something more general, which is like exactly what we want for type, you know, like overloading a function resolution and stuff like that. Because, you know, if you have some function that works on enum foo or bar, and another function works on foo or bars, for example, and then in your function you call some other function, and that function returns foo, but really it returns foo or bar, but just because it's the comptime context, it returns foo, then it's not like ambiguous which function is called. It isn't that this sometimes is a compilation error and sometimes not, and basically this switching over constant values can't happen accidentally. So the function resolution will still look for functions that work with foo or bar. Yeah. Okay. So I love how this looks. Like honestly, this is neat. Very neat. Yeah. So I don't even know what are next things. I think like for today, I'm pretty happy. And we basically, you know, we worked the new type system through the entire compiler pipeline. We had like new parsing stuff to do, which honestly was pain. We had type resolution and special casing recursive types and stuff like that. We're still struggling with recursive types in the rest of the pipeline, like for sure. But I think it's manageable. We are on a good path to make this work. Yeah, and I think I'm just gonna end it at that today. So look at these glorious type signatures, and I guess I'll see you here next time.